From the high desert in the great American Southwest, good evening, good morning, good afternoon, whatever it may be, wherever you are around the universe, whatever time zone, each and every one covered like a blanket by this program, the largest program of its kind in the entire world. Coast to Coast AM, I'm Art Bell. Great to be with you, my honor and privilege to be escorting you through the weekend. A very fortuitous guest coming up tonight, Sean Carroll, in light of the breaking news, which we'll get to shortly. First, a couple of, kind of personal notes, I guess. If you would like, take a quick trip up to coasttocoastam.com, click on Art's webcam, and there you will see what has been described as an explosive photograph. It is kind of explosive. That's Aaron. 8 months. 8 months, about to enter the 9th month. And, oh, my goodness. Getting a lot of comments on that picture, as you might imagine. And that's a keeper. Definitely a keeper in more ways than one. So get up there and take a look if you can. Now, we enjoyed Pizza Punch tonight. Finally, my order of Pizza Punch arrived, and we cooked the pizza in the oven tonight and used Pizza Punch, and it was delicious. Man, I'll tell you, the reviews coming in on Pizza Punch are absolutely incredible. Everybody's ordering again and again, and that's the mark. It was years in the doing, and it was something we were going to do for years, try to get Pizza Punch out, and we finally did, and it was just sort of a let's see how it goes kind of deal, one of those things. Let's get some product out and see how, what people think of it. I mean, that's what you've got to do with any new potential product. You've got to get it out and see what people think. Well, wow is all I can say. Wow. The reviews are just incredible. You want to see it, it's still in the initial sort of, get it out there and see what people think kind of stage, but it's all at artbellspizzapunch.com. That's ARTBELLS pizza, PIZZA, PUNCH, punch.com. artbellspizzapunch.com. Now, let's look at the world news and then the story that has me so excited. Wooing influential California Democrats, presidential contender Barack Obama vowed to turn the page on this Iraq disaster, while Hillary Rodham Clinton denounced President Bush's conduct of the war as one of the greatest blots on leadership we've ever had. California, long a major cash source for candidates of both parties, is poised to become more influential in the electoral process as well, having moved its primary to next February 5. Ooh, that's early. As a result, the state Democratic weekend convention was expected to attract all the party's presidential candidates, except perhaps Delaware Senator Joe Biden, who was campaigning in South Carolina. That's a biggie, and it's early. Nice to see the West Coast having an influence on things, finally. A car bomb exploded Saturday in the Shiite holy city of Karbala as the streets were packed with people headed for evening prayers, killing at least 58, wounding scores. Here's some of the country's most sacred shrines. Separately, the U.S. military announced the deaths of 9 American troops, including 3 killed Saturday in a single roadside bombing outside Baghdad, with black smoke clogging the skies above Karbala. Angry crowds hurled stones at police and later stormed the provincial governor's house, accusing authorities of failing to protect them from the unrelenting bombings, usually blamed on Sunni insurgents. It was the second car bomb to strike the city's central area in 2 weeks. President Bush, pushing for a hard-to-find breakthrough on a broad immigration overhaul, appealed to graduating college students in this diverse city, Miami, to help in persuading Congress to produce some kind of bill. The president gave the commencement address at Miami-Dade College, where more than half the students were raised speaking a language other than English. He gave the class of 2007 an assignment tell their elected representatives in Washington to get going on immigration legislation. Al-Qaeda-linked plotters hoped, apparently, to reproduce the September 11, 2001 attacks, planning to send suicide pilots to military bases and attack the oil refineries that drive the economy of Osama bin Laden's homeland, according to the government on Saturday, revealing new details of the purported plot. A government spokesman said some of the 172 attackers trained as pilots in an unidentified troubled country nearby, hoping to use the planes to carry out suicide attacks. Billionaire Donald Trump gave $10,000 to Governor Arnold Schwarzenegger to help pay off his campaign debts a little more than a month after the governor guest starred on Trump's TV show, The Apprentice. According to a campaign filing in an episode that aired March 18th, Schwarzenegger hosted 5 of the show's contestants in his private conference. All right, in a moment, we're going to talk about what I think is clearly one of the most exciting stories since I've been doing Coast to Coast AM. We'll be right back. Well, all right, there's a lot of news out there, but nothing that eclipses this, in my opinion. It's from the Daily Mail, but it's all over the internet, and I'm sure you've heard about it earlier in the week, but oh my. It's got the same climate as Earth, plus water and gravity. It's a newly discovered planet. It's the most stunning evidence that life, just like us, might be out there. Above a calm, dark ocean, a huge, bloated red sun rises in the sky, a full 10 times the size of our own sun as seen from Earth. Can you imagine that? 10 times bigger. Small waves lap at a sandy shore, and on the beach, something moves. That's the scene, or maybe the scene on what is possibly the most extraordinary world to have been discovered by astronomers, the first truly Earth-like planet to have been found outside our own solar system. The discovery was announced April 24th by a team of European astronomers using a telescope in La Silla in the Chilean Andes. The Earth-like planet that could be covered in oceans, may support life, is 20.5 light years away, and has the right temperature to allow liquid on its surface. Now, that's 20.5 light years. In other words, 20 and a half years to get there if you could do the speed of light. The remarkable discovery appears to confirm the suspicions of most astronomers that the universe is swarming with Earth-like worlds. We don't yet know much about this planet, but scientists believe that it may be the best candidate thus far for supporting extraterrestrial life. The new planet, which orbits a small red star called Gliese 581, is about 1.5 times the diameter of Earth. It probably has a substantial atmosphere and may be covered with large amounts of water, necessary for life to evolve, and most importantly, temperatures are very similar to those here on Earth. It is the first exoplanet, a planet orbiting a star other than our own sun, that is anything like our Earth. Of the 220 or so exoplanets found to date, most have been either too big, made of gas rather than solid material, far too hot or far too cold for life to possibly survive. On the treasure map of the universe, one would be tempted to mark this planet with an X, according to Xavier de Vos, one of the scientists who discovered the planet. Because of its temperature and relative proximity, this planet will most probably be a very important target of future space missions dedicated to the search for extraterrestrial life. Gliese 581 is among the closest stars to us, just 20.5 light years away, about 120 trillion miles, in the constellation Libra. It is so dim it can be seen only with a very good telescope. Because all planets are relatively so small, and the light they give off so faint compared to their sun, finding exoplanets is extremely difficult unless they are huge. Those that have been thus far detected, in fact, have been mostly huge. Massive, Jupiter-like balls of gas that certainly cannot be home to life. Now, this new planet, known for the time being as Gliese 581c, is a midget in comparison, being about 12,000 miles across. Earth is a little under 8,000 pole to pole. It has a mass 5 times that of Earth, probably made of the same sort of rock that makes up our world, with enough gravity to hold a substantial atmosphere. Astrobiologists, scientists who study the possibility of alien life, refer to a climate known as the Goldilocks zone, where it's not so cold that water freezes, not so hot that it boils, but where it can lie on the planet's surface as a liquid, water that is. In our solar system, only one planet, ours, Earth, lies in the Goldilocks zone. Venus, too hot, Mars, too cold. The new planet lies bang in the middle of the zone. Average surface temperatures estimated to be between 0 and 40 degrees centigrade, or in other words, between 32 degrees and 102 degrees Fahrenheit. Lakes, rivers, even oceans are possible. It is not clear what the planet is made of. If it's rock, like the Earth, then its surface may be land or a combination of land and ocean. Another possibility is that Gliese 581c was formed mostly from ice, far from the star. Ice is a very common substance in the universe and moved to the close orbit it inhabits today, in which case the entire surface will have melted to form a giant planet-wide ocean with no land, save perhaps a few rocky islands or icebergs. Surface gravity is probably about twice that of Earth, and the atmosphere could be very similar to ours. Oxygen, nitrogen. Although the new planet is in itself very Earth-like, its solar system is about as alien as can be imagined. The star's center, Gliese 581, is small and dim, only about the third size of our sun and about 50 times cooler. The two other planets are huge, Neptune-sized worlds called Gliese 581b and d. There is no A to avoid confusion with the star itself. The Earth-like planets orbit its sun at a distance of 6 million miles or so. I remember our sun's 93 million miles away, traveling so fast that its year is only 13 of our days. The parent star would dominate the view from the surface. If you can imagine a huge red ball of fire, it must be some kind of spectacular sight. It's difficult to speculate what, if any, life there might be on the planet. If there is life there, it would have to cope with higher gravity and solar radiation from the sun. Just because Gliese 581c is habitable doesn't mean it's inhabited. But we do know its sun is an ancient star. In fact, it's one of the oldest stars in the galaxy, extremely stable. If there is life, it has had many billions of years to evolve. Think about that. This makes this planet a truly prime target in the search for life. According to, and I want you to listen to this very carefully, Seth Shostak of the Search for Extraterrestrial Intelligence Institute in California, the Gliese system is now a prime target for radio searching. We had actually looked at the system before, but only for a few minutes. We heard nothing, moved on, but now we look again. By 2020, at least one space telescope should be in orbit with the capability of detecting signs of life on other planets orbiting nearby stars. If oxygen or methane, which would be telltale biological gases, are found in Gliese 581c's atmosphere, it would be good circumstantial evidence for life. Dr. Malcolm Freeland, a European Space Agency scientist, said the discovery of Gliese 581c was an important step on the road to finding life. If this is a rocky planet, it's very likely it will have liquid water on the surface. That means there may also be life. The real importance is not so much the discovery of the planet itself, but the fact that it shows that Earth-like planets are probably extremely common in the universe. There are 200 billion stars in our galaxy alone. Many astronomers believe most of these stars have planets. The fact that almost as soon as we built a telescope capable of detecting small Earth-like worlds, one turns up right away on our cosmic doorstep shows that statistically there probably are billions of Earths out there. As Shostak says, quote, "We've never found one close to being like Earth until now. We're finding that Earth is not such an unusual puppy in the litter of planets," end quote. But these alien Earths, well, are they home to life? No one knows. We don't understand how life began here on our world, let alone how it could arise anywhere else. There may be an awful lot of bugs and bacteria out there, but only a few worlds with what we recognize as plants and animals, or, of course, there may be nothing. The Search for Extraterrestrial Intelligence Institute uses radio telescopes to try to pick up messages sent by alien civilizations. Interestingly, at least 581c is so close to Earth that if its possible inhabitants only had our level of technology, they could just about pick up some of our radio signals, such as the most powerful military transmitters. Quite what would happen if we, for our part, did receive a signal is very unclear. Now, listen very carefully to this quote. There is a protocol, quoting Dr. Seth Shostak. Listen very carefully here. The president, he says, would be told first, after the signal was confirmed by other observatories, but we couldn't keep such a discovery secret, end quote. So, we now learn the president would, well, he'd hear first. So they would keep it from the public for at least a little while. Seth has never told me that. But in this article, he's quoted as saying the president would be told first. It may be some time before we detect any such signals, but it is just possible today that we're closer than ever to finding life in the stars. So I think that is about as exciting a story as I've ever read on the air, and I really did not expect that in my lifetime we would find another Earth-like planet. Now, this means that if we ever get close to traveling the speed of light, or even a healthy proportion of it, we could go to another world that would support our life. That's awfully exciting. To me. I don't know about you, but to me, what if it's a virgin planet without life? What if it is a planet simply awaiting inhabitants? I don't know which way would be more exciting. A planet we could populate with human beings, or a planet where we could meet other life forms that, well, according to this article, would have had billions of years of evolution ahead of us. Either way, really exciting. All right, I think we've got time to grab a call. We're going to do unscreened open lines. And then, as I mentioned, fortuitously, in the next hour, Sean Carroll is here. Sean Carroll is a senior research associate in physics at the California Institute of Technology. He's going to be talking about theoretical physics, astrophysics, focusing on issues in cosmology, field theory, and gravitation. Now, with a discovery like this, he'd be the guy you definitely want to talk to. Let's grab a quick call. We'll give you the numbers as we come back from the break. But right now, Wildcard Line, you're on the air. Hello? Wildcard Line, you're on the air. Going once. Going twice. Gone. Let's try another wildcard line. You are on the air. Hi. Oh, this is interesting. I'm not getting audio. Hello back there in California. No audio. Somebody's going to have to throw a switch back there, or something has abandoned us. I will try one additional. Wildcard line number 3. You're on the air. Hello.
Hey, Art. How's it going?
Much better now. I have you.
Good. My name is Clark, calling from Ontario, Canada.
Yes, sir.
I'm an undergraduate physicist and working towards a paper that I believe you'd be quite interested in if I could take a moment to give you the synopsis of it.
Very quickly, sure.
Okay. Well, basically, what we discovered is something to satisfy the solution you were just talking about, which is how to approach light speed. And it has to do with a breakdown of relativistics. And essentially, what I believe had been thought by Einstein. Whether or not he came to it, I don't know. But it seems that it has to do with interfacing with matter on a very unique level at which you can manipulate the actual way that gravity flows through it, if you follow me.
Not yet. I don't follow you yet, but I hope to. So what I will do is hold you over the break. We're coming up on a break very rapidly here. So
Sure.
I'll hold you over, and I'll try to break it down for me in language that everybody will understand, okay? Good. Hold it right there, and we will be right back. That really is an exciting story, my God. We've found another planet like Earth. The implications of that, and it being billions of years ahead of us, not millions, but billions of years ahead of us, and in terms of possible evolutionary building time, that really is exciting. And, you know, they indicate that unless we're specifically looking, even if we were specifically looking for signals, or they would barely be able to hear, assuming they were aimed right at us, our strongest military radio transmission. So getting something outside the Earth's atmosphere in terms of a radio telescope that'll look for signals, I'll tell you, this is the first place I'd be pointing. How about you? We'll be right back. Well, all right, back to our caller, and you were talking about as fast as light, or do you contemplate even faster than light travel as being possible?
Well, that opens up a big can of worms.
All right, well, let's deal with the can we've got open right now. You're talking about traveling near the speed of light. Let's stick with that. How would you do it?
Well, I didn't actually say that, but if you want to stick with that kind of can of ideas, sure.
Okay, well, no. I want to go with your can. What is your can?
Oh, okay, well, the can actually can produce the results of all of the above that you said, first of all. Now, each one of those will have a sort of proprietary technique for achieving the same.
Meaning what? You can't tell me about it?
I can tell you about some of it, but this is all time pertinent. If I was on for 3 hours, we could go into a lot of it, and some of it I can't talk about. But what we could is much detail. So
tell me what you can.
Right.
Titillate me.
Do you remember, this would be extremely helpful for my research as well, and it's going to corroborate with what we're talking about. But do you remember interviewing an ex-admiral that was associated apparently with the Philadelphia experiment? And he was talking about time anomalies and doing experiments with mechanical clocks and cameras inside time bubbles. Do you remember that?
I kind of recall that, yeah.
Yeah, okay, well, that's important, of course. And this is sort of going into some fuzzy areas that haven't been well calculated out, you could say.
Now, I asked you during the break to think of a way you could explain it so everybody would understand.
Right. Okay.
Proceed.
Well, this isn't exactly easy, but I'll do my best. If you can imagine, for example, the gravitational constant, which allows things to fall at 32 feet per second, correct?
Okay, yes.
Or 9.81 meters per second squared. This relates to an unknown phenomena called gravity, which, as you can appreciate, is still being heavily researched, and the particle called gravitrons is in part supposed to be responsible for this effect, correct?
Well, I'm not sure. I mean, gravity is a function of mass, right? I don't know about gravitons.
Well, graviton is a particle explanation for a phenomena, including the gravity wave, which is part of the particle sort of duality and the wave-particle duality problem that's going on right now, which in this would circumvent the need for either particle or wave. It would actually supersede, and this is sort of some of the new theories that are coming out. Of the most important of those new theories is one called the causal dynamical triangulation theory, which is talking about the absolute Planck size space. And what we mean by that is 10 to the negative 34, which is a size, very, very small. It's the smallest size you can possibly ever get to, according to current physics. And at that size, they're saying we've come to a new model for what that might be. And it brings us all the way back to the school of Pythagoras, which talked about 7 sacred, and by Pythagoras' means it was in fact holy and divine to speak about them, which was the 7 Platonic solids.
All right, listen, I'm going to stop you here and say you have not succeeded in explaining this way the average person could understand it. You're kind of all over the place, but feel free to send me an email and see if you can explain it. And if you can, who knows? Maybe we'll have you on the air. Maybe you're on to something, but I couldn't tell from what you just said. So I'm available, artbell at AOL.com or artbell at mindspring.com. Fire me off something, and we'll go from there. East of the Rockies, you're on the air. Hi.
Hello, Art. I just had a really quick question. With all the theoretical physics guests that you have on recently,
Yes.
I was just wondering, will Dr. Kaku ever be on again?
Sure. How's that for a fast answer? Sure.
Okay, because I noticed he hadn't been on in a couple of years, and I was just wondering if everything was still in good standing with him.
Oh, absolutely. Sure. Yes, we will have him on again. I have done so many interviews with Dr. Kaku that we have covered pretty much of the material that he has. And so we're exploring other theoretical physicists to see what else is out there in the world. But we'll get around to Dr. Kaku again, sure.
All right, thanks.
All right, you're very welcome. Take care. Dr. Kaku is the co-founder of string theory and a brilliant man, to be sure. But I thought we might want to take a look at what the rest of the world of theoretical physics has to offer, and that's what we've been doing. Wildcard Line, you're on the air. Hello.
Yes. Good evening.
Turn your radio off, please.
Yes, Art, it's off. Good evening,
Okay.
Art.
Hi.
Congratulations to you and Aaron and your coming baby, and all blessings upon you, Art.
Have you seen that photograph?
Excuse me?
Have you seen the photograph?
No, I haven't. I'm not on the computer. I would like to see it, though.
Yes, you would.
Yes, sir. Art, several weeks ago you'd posed the question, does evil exist outside of us? Or does it exist only within us? Does it
That's
exist
right.
outside of us as a separate entity?
That's right.
And I would certainly propose to you the idea, which I found to be true through about 25 years of research and a lot of curiosity leading that research. And I have found that the global elite who control the economy as well as own the economy of the planet all have one thing in common, and that is that they take their religion very seriously, and that their religion is referred to in nomenclature as the Luciferian doctrine, and that they worship Lucifer, and they serve Lucifer, and they believe Lucifer to be a true reality and actually Almighty God himself.
Yeah, but how do you know a lot of them aren't Catholics, Jews, Protestants, whatever?
Excuse me?
I said, how do you know a lot of them are not Catholics, Jews, Protestants, whatever?
Actually, they are, Art. Actually, they are. And, it's
And Luciferians at the same time?
only in name do they refer to themselves as other than Luciferians. They refer to themselves as Luciferians among themselves. And they do control our society in this country as well as throughout the world. And through the multifaceted beast of what is referred to as social engineering, thus we see manifested the evils of the crimes against one another, the war and the crime and everything else that you would think of as what's going wrong in society. These things are done intentionally to bring about a certain result.
You think it's their fault?
It's at their instigation that our reality is in the negative the way that it is. These things are implemented intentionally by them through a Hegelian dialectic philosophical means in order to gain a certain result. They create certain conditions out of which a result will come. Their main objective in actually bringing the world down 5 notches is to bring it into, in a docile way, into the New World Order of nations in which there will be no more national sovereignty.
Okay, I've always wondered about this. I don't understand why everybody always thinks that those who run everything, these international elitist New World Order people that they talk about, always want the world, our nation and the world, to fail. That's very bad for profits. Very, very bad for profits. It's better when things are going along swimmingly and when industry is doing well and there's lots of trade, and that's how they make their money. Why would they be plotting this external evil influence that would cause man with free will, which I believe, by the way, to begin doing terrible things and ruining the world? It has never made sense to me, and you always look for motive in everything, and I find no motive. If they exist, as he stated, and I'm not acknowledging that they do, but if they do, certainly they wouldn't want to ruin everything because that would ruin their bottom line. First-time caller line, you're on the air. Hello. Going once, going twice, gone. West of the Rockies, you're on the air. Hi.
Hello?
Hello, turn your radio off, please.
Okay, hold on a second.
That's something to remember, all of you. When I say you're on the air, instantly turn your radio off.
How's it going, Art?
It's fine.
Is this Art?
Yes.
Okay, basically I have a story about the undead. I don't know if you're familiar with that topic at all.
I am indeed.
Oh, you are?
Oh, sure.
Oh, okay. It was like a very striking circumstance that took place. I was deserted, basically, in between Las Vegas and Victorville, California.
There are many undead in that area.
There is?
Oh, yes.
Oh, my God. Like, I didn't know that.
It's what I call the Baker Triangle.
The Baker Triangle.
Oh, yes. Cars mysteriously stop and overheat in that area, and of course, leaving many undead wandering. I think we lost him. He's gone. Yeah, okay. East of the Rockies, you're on the air. Hello.
Hey, Art. It's Corey in Minnesota.
Hi, Corey. You have anything for us on the undead?
Oh, no, I didn't.
No.
But you'll be curious to hear this. I was listening to replay of Terrence McKenna from 97.
Yes.
And you mentioned that 95% of the bees were gone. You referenced a news story. It was in the last hour of the open lines, like 3 minutes into it. I don't know
Way back with Terrence, I said that?
10 years ago, 95%.
That might have been, sir, a regional thing, but certainly not national.
Nope.
With
you said
we've
world's
got 27 states now affected here in the U.S.
You said the world's honeybees, and you even grabbed a piece of paper. You should go back and check it out. It was on.
You're right. I will. I certainly will.
Hey, and don't you think it's funny that after last weekend, someone accused Seth Shostak of being a disinformation, specialist? They come out and release this information, make him a hero. I don't know. I just thought it was funny.
Well, listen. I'm the one who has always argued with Seth, and I think it was Seth who said, again and again, that everybody would know right away, instantly, if there was contact with radio contact from another civilization. It couldn't be held secret at all. Now, he's quoted in the Daily Mail article as saying that, indeed, there is a provision for the president to be notified first. And then he does go on to say it would be confirmed by other observatories, but we could not keep such a discovery secret. I'm not so sure. I never have been, and I remain unsure. I think that kind of thing could and would be kept secret for some time. Wildcard line, you're on the air. Hi.
Hi, Art.
Hello.
Hey, I've got a question about the SETI ordeal. If they found a signal and the government told them to be quiet about it, do you think Seth would go public, or would he be a company man and do what they say?
I really can't comment on what Seth would do. I just don't believe that the public would be told right away. I've never believed that, sir.
Yeah, I think you're right. I mean, they've got a lid on the whole UFO situation, too, so they probably want to keep a lid on that one as well.
Oh, look, our government operates on secrecy. It's the currency of the realm. Yeah. So my opinion is it would be held secret, it would be discussed, and whether or not to make it public would be a heated argument indeed.
Yeah, I think you're right about that. But I'm just maybe we get lucky and one of the SETI people would go under their shoes or under the rug and sort of feed info to the media or something. I don't really know much about Seth's character, but I think
okay,
that would be the right thing to do.
Well, so do I. The answer is that I do, in a way, agree with Seth. In other words, as various observatories were called upon to confirm the finding or the signal, that eventually word would leak out. But I think that for a while, for a period of time, particularly depending on where the signal came from, how close it was deemed to be. In other words, if it was 20 light years away, well, they might tell us. If the signal appeared to be a lot closer, my opinion is it would be a matter of national, if not world security, and it might be some time before we'd hear about it. West of the Rockies, you're on the air. Hi.
Well, hey, Art. This is not a bootlicker. Just wanted to say hi to you, and I had a great guest idea.
Okay.
Mr. Larry Spring, a 92-year-old physicist, because I know you like scientists.
I do.
He's at LarrySpring.com. He's got all those free energy devices you crave so badly.
Well, does he have any of them working?
Yes, he has all the small models in his shop up north in Mendocino. And he gives lessons every Saturday and Sunday to the children that show up.
Well, I hate to be the doubting Thomas, but it ought to be all over the news. Anything that actually runs on free energy, that
he's 90,
ought to be
he's
big.
92.
I don't care how old he is.
It's hard to get out, you know.
I don't care. I mean, if he really has demonstrated this and has the real McCoy, it should be in the news everywhere.
He has a patent on the spring atom, too.
The spring atom.
Don't ask me what it is. I have no idea.
Okay. Well, maybe who knows? Maybe we'll ask him. But my opinion is that if there really was a free energy device, anything so little as a toy that kept going and going, leaving the Energizer bunny huffing and puffing in the rear, well, we'd all know about it. Let's go to the wild card line and say good morning. You're on the air.
Hi, Art. This is Cheryl from Milwaukee, Wisconsin.
Hi.
Hi, and I'm calling to congratulate you on the soon-to-be-here little Asia.
Thank you. Have you seen the photograph?
No, I'm not able. I do not have a computer yet. And then
Yikes.
I don't have a computer yet, but I sure would have liked to see that. And I have I say predicament. I mean, not predicament. I say that in about 15 to 16 months, you're going to have another little girl, and her name may be Asia. I mean, not Asia. Ariel Bell.
Ariel, huh?
Ariel.
Well, no, I think one is going to be it for some period of time.
Oh,
so.
Probably. I'm a cat lover just like you too, and I was wondering what little Dolly and Abby and the other one what
Yeti.
they look like. Yeah.
What they look like. Well, again, if you had a computer, you'd know that because I'm posting pictures of little furballs all the time. Abby and Dolly get along. Oh, they're fast friends. Very fast friends, as those of you with computers have seen. Yeti holds himself above Dolly to some degree, and Dolly is jealous of Yeti, and whenever Yeti comes near me, Dolly runs over and swings her little paws at him, driving him away. Now, I don't understand how that's occurring, because Yeti is at least 4 times the weight of Dolly and could easily trounce Dolly, but doesn't. Wildcard line, you're on the air. Hi.
Hi, this is Jeff from Bountiful, Utah.
Yes, sir.
How are you?
Fine.
I just wanted to ask you, if the government is actually concealing the fact that we've been visited by alien beings, why would they do so?
Well, because it would shake a lot of people's faith, for one reason. A lot of people believe that we came here, as was described, sir, in Genesis, and that we are the only ones, and that there would be others would kind of shake the foundations of what they believe. How's that? Hello? No? He's gone. Yeah, he's gone. Well, that's my opinion. That's not the only reason. Another very, very, very good reason that we've discussed any number of times here on Coast to Coast AM is that our government really can't do anything about it. If these things are traversing our atmosphere at 25,000 plus miles per hour successfully without burning up and turning into little piles of jelly. That means they can do things we haven't even thought about doing yet, including stopping them, shooting them down, or otherwise affecting them. And governments don't like to admit to their constituents that there are things going on that they cannot have an effect on. So that would be another reason. Basic religious foundations might crumble. People's faith might crumble. Governments might tumble. I don't know. Just a few reasons. I'm Art Bell, and we'll be right back. Oh, what a good guest at a good time. Sean Carroll is a research associate in physics at the California Institute of Technology. His research involves theoretical physics and astrophysics, focusing on issues in cosmology, field theory, and gravitation. His current research involves models of dark matter and dark energy, cosmological modifications of Einstein's general relativity, the physics of inflationary cosmology, and the origin of time asymmetry. He's received research grants from NASA, the Department of Energy, and the National Science Foundation, as well as fellowships from the Sloan and Packard Foundations. And with the discovery of a new planet just 20 and a half light years away with Earth-like conditions, what a great moment to have him on. We're back with him in a moment. Sean Carroll, welcome to Coast AM.
Hi, thanks for having me.
Oh, it's great to have you. Listen, this is such a big story. I'm referring to the discovery of this Earth-like planet. Have you read the story?
Yeah, I know a little bit about it, absolutely.
Oh, man, I didn't think they would ever discover one in my lifetime, but here we've got one with similar temperatures to Earth, probably with water and atmosphere. It's just amazing to me that we have, if you can tell me, how did we make these determinations?
Well, I think that's a great question because they're very, very indirect. And in my specialty of cosmology, we're very used to making a lot of conclusions on the basis of very little data, but backed up by our huge amount of confidence in the laws of physics.
Right.
And that's very much what we did here. We looked at, the royal we, meaning all scientists in the world, a team of European astronomers looked at the motion of this star, Gliese 581, I guess it is. And, of course, what's going to happen is as the planet orbits around the star itself will orbit a little bit in response to that because Isaac Newton says that for every action there's an equal and opposite reaction.
Mm-hmm.
So the original star is moving ever so slightly back and forth. And what that means is that the light that is coming to us from that star is Doppler shifted. It's squeezed in its wavelengths when it's coming toward us and then stretched when it's going away,
Sure.
ever so slightly.
Sure.
And from that, we can infer that there are things orbiting this star. In fact, this is a whole solar system. I'm not sure how much has been made clear, but there's 3 planets orbiting this star. One of them is small enough to be potentially Earth-like and at the right distance, but there's also 2 other heavier planets, so this is quite an interesting system overall.
Well, they say here that this is a very old star, I guess, and it would this planet would have had billions of years of possible evolution ahead of us.
Yeah, it's a very small stars burn their fuel more slowly, and therefore they last longer. So the amount of time you have for anything to happen around a smaller star is going to be a much longer time. Our sun is a medium-sized star as sizes go, but as numbers go, there's a lot more smaller stars than there are bigger stars. So this is probably a pretty typical thing. I would say that the exciting thing here is not necessarily this particular planet, although it is exciting, but the fact that this is one of the 100 or so closest stars to the sun where we found this planet. And there's 100 billion stars in our galaxy. So if we're allowed to extrapolate, which we're not, but if we were, this is saying that there's of order 1 billion such planets in our galaxy.
Well, you can do that on this program.
Okay, that's good.
Speculate
in other words, we would not be surprised if it turned out that in the Milky Way galaxy there were 1 billion planets that satisfied these criteria. And that's the amazing thing.
Yeah, so if life, given a certain set of circumstances, a good atmosphere, reasonable temperatures, and water, I'm not sure what else there would have to be, but if those things were there, and life is common, that's the one big question that we don't know. I mean, they say right here it's habitable, but whether it's inhabited, whether there's actually any habitation or not is another question altogether. There may be no life anywhere else, but that's not very likely, is it?
Well, I have no idea how likely it is, but we learn more and more by making observations like this. What we know about this particular planet, I wouldn't even be willing to say that it's habitable. It has the right distance from its host star to have a habitable temperature. But this is still a very different planet from Earth. It's a little bit heavier. It orbits its star once every 13 days, so it has a 2-week-long year. We have no idea how long it takes for this planet to rotate on its own axis. So for all we know, it might be tidally locked. Just like the moon always shows the same face to the Earth, this planet might always show the same face to its star. And it has these 2 giant planets also in the solar system. The inner one has a period around the star of only 5 days. So once every 5 days, you see this planet zipping around its star. And also, the star is a variable. The star is not almost precisely constant like the sun is. It fluctuates ever so slightly. So this is a wild system to be on. There's a lot of variety in the universe. But nevertheless, maybe even with all those things, maybe this planet has an atmosphere, maybe it has water. All of those things are quite possible knowing what we know about it. So, we don't know. It could be that life happens all the time. It could be that life is so rare that you would need 1 billion planets before you had a chance to get one of them with life on it. But this is how we find out. We make the measurements. We now are learning more and more about how frequently this happens, under what conditions it happens, and obviously we're going to be listening in to that system to see if we can pick up anything.
Seth Shostak from SETI said that they had very, very briefly taken a look at this star, and they didn't hear anything, but it was a very brief look. And now, obviously, with this discovery, he says they will now go back and take a very intense look and listen, as it were.
Sure. I mean, it's the natural thing to do. If there's only one other person in your extended network, as MySpace says, then you're going to look there. But I don't know. I mean, my own guess is that it's very, very unlikely that there is the kind of life on this planet that we would notice by tuning in our radio telescopes, just because I think that if that kind of life were all over the place, we would have already noticed by tuning in our radio telescopes somewhere. But I admit that that's just a guess. It's a feeling based on the statistics, but I would be very happy to be proven wrong, so I'm very enthusiastic for those guys to go and listen in as well as they can.
Well, they make a comment here that if there was life there and they were at our level of technology, and I would assume they'd be beyond us if there was life, but if they were at our level of technology, they might be able to just hear some of our strongest military transmitters.
Right. But like you say, the chance that there are at our level of technology is very close to zero. We've only been at our level of technology that we were able to build a radio telescope for less than 100 years.
Right.
So if they're 1 billion years past us or 1 billion years less evolved, then they're not very close. We're at a very, very interesting and special time in the history of the human race. We're on this very, very steep trajectory of technological development. And hopefully we'll keep going. We could crash and burn. We don't know any of these things. What we do know is that it would be really, really surprising to find another solar system with life that was about tied with us. They'll much more likely either be way ahead or far behind.
Could we survive on that planet? Given the assumptions being made about this planet right now, that it might have, or perhaps double the gravity we have. Would we be able to survive?
We don't know enough to be able to say that. I mean, certainly you can survive in double the gravity exactly as well as you could survive if, someone put 100 or a couple hundred pounds on your back. It would not be fun. It would not be good. You might not have a long lifespan. We have no idea what the atmosphere is. The temperature range seems to be good. It's about like Chicago, actually, the temperature range. But the atmosphere could be anything. The amount of water on the planet could either be negligible or it could completely cover the surface. So it's possible, it would be uncomfortable, and it might be completely unfeasible. But still, this is only 1 out of 100 planets we're talking, 1 out of 100 stars we're talking about.
Okay, quick question. Based on what you just said, that our survival rate at double the gravity might not be as long, at less gravity, at, say, a third or a fourth of Earth gravity, would our survival rate be, our longevity rate be better than it is here?
Sadly, no. The human race is more or less evolved to live in one Earth gravity. And the reason why we know this is because when people spend too long in orbit, they get sick. Their bones begin to deteriorate. It's very, very hard to live in a weightless environment for months at a time.
And that same thing would apply to a fraction of the gravity.
You would imagine that, it would apply a little bit less if you had a little bit less gravity, et cetera, et cetera.
Okay. Well,
it's not surprising that we're tuned to live at a certain kind of gravity. I mean, maybe one could adapt over generations and generations. But the real reason why any individual planet that we find elsewhere in the universe is unlikely to be directly habitable is the atmosphere.
How much of a buzz has this set off in the cosmological community?
Well, it's this is the same to cosmologists as it is to every other human being. It's very, very exciting. Cosmologists, think big. We think about the entire universe all at once, and a little tiny planet is beneath our notice. But still, it's a planet that is has the right characteristics to have atmospheres and water. So we all think this is fantastic.
And I really did not think in my lifetime that we would make this discovery. Did you think we were that close?
Well, I knew it always surprises me how quickly we go. I thought, the first planet that was detected outside outside our solar system was when I had already gotten my PhD, which in my personal universe doesn't seem like that long ago. It was less than 15 years ago.
Sure.
And now we have over 200 that we've discovered. So I think that this is something it's not smart to bet against. The rate at which we're getting better and better at this is amazing. And my colleague at Caltech, Mike Brown, is responsible for half of these planets being discovered, I think. So I think it's great news we've discovered one that is a bullseye in terms of plausibly being the kind of thing that could support life. Of course, there's also interesting things right here in our solar system that one could imagine are hospitable to life. I doubt that they have life, just because I think there's probably a rare event. But we have a lot of exploration to do right here in the solar system with moons of Jupiter and moons of Saturn, for example. And these more detailed astronomical observations of other stars are going to continue to teach us a lot. So I'm not placing any bets one way or the other on what we discover in the next 10 years, because I'm bound to be surprised.
Doctor, if we had a radio telescope in space, or perhaps even better on the far side of the moon, how much better would our ears be?
I think that radio telescopes do pretty well here on Earth, because for the most part, radio waves can penetrate through the atmosphere. Other kinds of telescopes, if you have ultraviolet telescopes and various other things, then they do better in space. Even radio telescopes do better in space. But I think the constraint here is not space versus Earth. It's just time spent and number of telescopes doing the work. And it's hard to convince people to spend money because it's a long shot, You're saying, well, spend several $1 billion or $1 million at least, and maybe you get something, maybe you don't. This is never a good sales pitch. But obviously, if you get something, it's a high payoff.
All right, Doctor. Quick question. It's 20.5 light years from us, which would mean traveling at the speed of light, it would take 20 and a half years to get there. Now, what is our current technology? In other words, if we wanted to send something toward this planetary system, with a slow but steady acceleration of some sort, I'm not sure what the best technology for that would be. Well, how fast could we get something going, and how long might it take us to get something there?
I'm not going to make a guess at any numbers because I don't have any reliable information about that. But, let's tell the truth. Right now, we cannot put a person on the moon. We used to be able to, but we lost that capability.
Yeah.
So, on the other hand, that's sort of the bad spin to put on it. The good spin is that it's a technology problem, and technology problems are always solved eventually. If we wanted and put a real effort into space propulsion, then in some number of years, which is probably a large number to be honest, but in some number of years we would be able to build a ship that will visit other stars. It will take a very, very long time. It's not going to take 25 years to get there. It's going to probably take centuries.
Centuries. Okay, let's back away a little bit and approach some other subjects like the Big Bang, which I love. I love the subject of the Big Bang. You are, I take it, a believer in the Big Bang theory?
Oh, yes.
Is it still called a theory, by the way, Doctor, or is it now an established, settled fact?
We in science always call things theories, even when they're established beyond reasonable doubt. We talk about the theory of relativity, or we talk about Isaac Newton's theories, or quantum theory. So the Big Bang, not the point itself at t equals 0, at 0 time, where everything is infinite, because that's something we don't understand. We admit that. But the Big Bang model, the model that says that we live in a big universe that is expanding from an initially hot, dense state over 10 billion years ago, that's established beyond reasonable doubt. Either you believe in that or you're on the fringe as far as science is concerned. So we call it the Big Bang Theory, but there's no respectable scientist who doubts that the Big Bang is basically true. We have a lot of work to do in filling in the details and fascinating questions about the very beginning of things, but the basic framework is solid.
So, pretty settled belief.
Yes, that's right. It's been tested a million ways from Sunday. We have data. We've made predictions. The predictions just keep coming true over and over again.
I've never been able to conceive, nor can I now, how all that is came from something smaller than a quark, something that just happened.
Well, that's okay. Why should we be able to conceive it? The universe is a big place, and we grew up, hunters and gatherers. We did not grow up, evolution did not select us to think about the mysteries of where the universe came from. So it's, science that is enabling us to learn things that stretch well beyond anything in our everyday experience, and to be much more surprising if those things that we learned turned out to make perfect sense and just seem, well, that's a natural thing, rather than being absolutely astonishing. And the truth is, when we get to learn about relativity and quantum mechanics and the Big Bang and black holes, we're astonished over and over again, and that's how it should be. But we should also be very, very hard-nosed about these ideas. These ideas are fun and intriguing, but we don't say that they're established beyond reasonable doubt until they've passed an incredible battery of tests. And then, once they have passed those tests, you have to say, all right, this is what the universe is telling me. I'm going to deal with that and try to move beyond it.
Okay, what is it that makes us so convinced that there was a Big Bang? I know there is the lingering radiation from it that we can apparently measure, and there must be more.
That's right. There's a series of things. The first thing is that Einstein's theory of general relativity, which has been tested in many, many ways itself, basically says there's almost no other choice. That if you have a universe filled with the stuff that we think is in the universe, and then it's either going to be expanding or contracting. You have a 50-50 chance.
All right, I'll tell you what, Doctor, hold it right there. I see that we're upon a break. My guest is Dr. Sean Carroll, and we're talking about this new Earth-like planet that's been found, and now we've sort of moved on to the Big Bang, the beginning of it all, I guess, since it still is a theory, well established, but indeed still a theory. From the high desert and the great American Southwest, I'm Art Bell. Here I am. The Big Bang has always been, as I'm sure it has been for many of you, an absolute fascination for me. After all, it's how everything, time, all the suns, all the planets, everything that is here and out there became. Before that, we have no idea what was, if anything. Certainly no time. There was not time. There could not be time until you had at least a couple of objects that you could measure against each other, relative motion, distance, that sort of thing. So prior to that, there could not have been time. Actually, we don't know what there was or wasn't. We'll be right back. By the way, I do review all the emails I get, and the featured article on coasttocoastam.com is one that I received from a listener and sent on to the webmasters of coasttocoastam.com, and it is graphic. This particular video is really scary. It was taken in a parking lot, and it's a bunch of dying bees, just flopping around on the ground. And the person who sent it to me, I don't know, I just reacted in a kind of a horrific way watching it, and I'm sure you may as well. You may want to see that. It's right on the front page of Coast to Coast AM, and it was sent to me a couple of days ago, and I sent it on to the website, and I see they've got it up there. All right, Dr. Carroll, welcome back. The Big Bang again. We were talking about the evidence that supports the whole concept of a Big Bang, and there is, we covered it already, the background radiation that we can measure.
Mm-hmm. Well, and it gets even better than that.
Okay.
We have great evidence that the universe is expanding, of course. This goes back to the 1920s. Faraway galaxies are moving away from us, and the further they are away, the faster they're moving. But then what we can do is take the laws of physics that we think we understand, and we can extrapolate backwards. We can say, if this is the universe we see today, what was it like when it was 1 second after the Big Bang? And the answer is that 1 second after the Big Bang, it was a nuclear reactor. It was undergoing nuclear fusion, just like is going on in the sun today. So it was turning protons and neutrons into helium and lithium and deuterium. And you can make a prediction. You can say, all right, given everything that we know about nuclear physics, everything we know about general relativity and cosmology, how much helium should you have? How much deuterium should you have, et cetera? Okay. And then you should go out and measure them, and you get the right answers.
All right. Well, here's a part of it that doesn't make sense to me.
Okay.
If we have an explosion here on Earth, you get a very high velocity of small particles moving in all directions very quickly. And then, of course, as time from the explosion goes on, they begin moving slower and slower and slower and finally fall to Earth because of gravity. Now, in space, you don't have as much resistance from atmosphere and anything else. So one could imagine they would continue to move out at perhaps the initial velocity or slightly less or whatever. But I'm hearing that things are expanding at an ever faster rate. That doesn't make sense.
Well, good. I'm glad it doesn't make sense because it was a big surprise when it was discovered in 1998, only a little while ago. We're approaching the 10-year anniversary of this. You're right. You would expect there's no resistance whatsoever in space, of course, but what there is gravity. So every galaxy and every particle in the universe exerts a gravitational pull on every other particle in the universe, and what you would expect is that everything is expanding, but it's expanding ever more slowly.
Right.
The expansion of the universe should be decelerating.
Right.
However, there are things in the universe other than particles. So Einstein, long ago, proposed the possibility that even empty space itself could have energy. So not only is there particles moving through space, but space itself has a little bit of energy.
Okay.
And they worked out way back then that if this idea were true, then what would happen is that things would eventually begin to accelerate away from each other. That energy of empty space would provide a perpetual impulse that makes the universe expand faster and faster.
But why in one direction, always away from the initial Big Bang? If there's energy there, one would imagine it would act, well, I don't know, not only in one way on what was initially, in other words, you fire a bullet, it slowly decelerates, right?
That's right. But you have to remember...
It's poor analogy, but what I'm saying is, okay, there's energy. Why isn't the energy slowing the expansion?
Well, so there's two things. One is that there is no directionality anywhere in the Big Bang story. Every place in the universe looks more or less the same, and every direction looks more or less the same. This was not an explosion within a pre-existing space. This is space coming into existence and then getting bigger and bigger.
Okay.
So it gets bigger in the same direction everywhere. But, okay, so that, I think, is an important part of the Big Bang story that we've understood for a long time. You're putting your finger on a very interesting thing, which is that it's easy for me to say there's energy in empty space, and you could even sort of let me get away with that, but then you say, why does that make the universe accelerate?
Right.
And the answer is that Einstein's version of gravity, Einstein's new understanding of gravity that replaced the old Isaac Newton version, says that what gravity really is the curvature of space-time. That space and time are a thing, and they have a geometry, a dynamics, they can be warped and stretched, and the thing that warps and stretches space and time is energy. So the important thing about the energy of empty space is that it doesn't go away. Ordinary stuff, when the universe expands, it dilutes away. It gets fewer and fewer particles per cubic light year because everything is moving apart. But the energy of empty space remains at a constant energy per cubic light year. There's a certain amount of energy, and even though space is getting bigger and bigger, the amount of energy in every cubic light year stays the same. So you just plug that fact into Einstein's theory of relativity, and he says, therefore, the curvature of space-time doesn't go away. It keeps getting this push from the energy. And what that manifests itself as is distant galaxies accelerating away from us, faster and faster. This was all understood as a possibility a long time ago. People knew that if there was energy in empty space, it would make the universe accelerate. And the fascinating discovery in 1998 was that that's actually what is happening. It's not just a hypothetical thing. We can see distant galaxies moving away from us faster and faster.
Okay, but I still don't grasp why the energy doesn't push things left, right, or back toward the original point of explosion. In other words, why is the energy always pushing things away?
Well, there is no original point of the explosion. It's all of space came into existence in the conventional way of telling things. And, I mean, all I can do is tell you what Einstein says, because he's been tested and proven right. He says that if you have a little cubic centimeter of space, think about a little version rather than a light year.
Okay.
You have a cubic centimeter of space, and it has energy in it. And basically, if that energy doesn't go away, it provides a tension. So if you have a piston full of this stuff and you pull on the piston, it will pull back. It has a negative pressure in a technical term.
Right.
And basically that little persistent cubic centimeter of energy is providing a curvature of space-time that makes two particles that you put in that cubic centimeter begin to move away from each other. And at some point, you're just going to have to trust me.
Okay. Space and time came into existence simultaneously.
Well, good. This is another very good question, and this is the kind of thing that professional cosmologists are beginning to talk about more and more. There are two different things. There's the sort of conventional story that we tell each other about the Big Bang, but then there's speculations beyond that. So the problem is that really the Big Bang is a point at which we don't know what happens. It's the point at which general relativity, this wonderful theory whose praises I've just been singing, completely breaks down and predicts that the theory itself can't possibly be right because it starts giving you infinite answers. So the correct story of the Big Bang is going to have to be told within the context of something that goes beyond Einstein's theory of general relativity. Either quantum gravity, which we don't have yet, or some new theory that someone has to invent. So I can tell you the story within general relativity, and I can say things like space and time didn't exist before the Big Bang, but I know that the story according to general relativity isn't right. So we're speculating these days about what happened at and before the Big Bang. It might be that that was the beginning. It might be that that was the origin, that there wasn't any such thing as before the Big Bang. Or it might be that there was a universe before the Big Bang that gave birth to our universe as a little baby universe. There was some event within space and time that already existed. So when we're honest, we have to say that's one of the things we don't know about. We know very well what the universe was doing 1 second after the Big Bang, but at the Big Bang, we're still speculating right now.
Okay. So, again, asking time came into existence, you believe, as the Big Bang occurred, and we had objects suddenly moving, and measurements were possible, and velocities could be determined, and all the rest of it. Before that, before things were there could not really have been time as we understand it, could there?
Well, yes, there could have. So,
there could have.
According to the conventional story, the answer would be no, there could not have. But we know for sure the conventional story is incomplete. So if I only speak within the world of what we already understand, there's no way that there could have been something before the Big Bang. But we also know that we don't understand the Big Bang. So if we're more honest, we have to say, well, that we have alternatives. Maybe there was something before the Big Bang, or maybe there wasn't. Both of those are perfectly plausible. We cannot use pure reason at this point in our intellectual development to decide between them. We have to keep both options open and try to see whether or not we can reason from what we do observe in the observable universe to what kind of story would make sense for what happened before the Big Bang. Was there a universe before the Big Bang, or did everything come into existence? And both alternatives are very energetically pursued right now and very passionately championed by people who like one or the other.
So there could have been just empty space.
That's
prior
right.
to the Big Bang, right?
There could have been empty space. There could have been a pre-existing universe with intelligent life in it, or there could have been nothing at all. These are all on the table in terms of the possibilities.
Is there anything that explains how something the magnitude of a Big Bang could actually even occur? Anything that doesn't, or even does, include a maker, a God?
Well, as scientists, what we're looking for is an explanation that is as simple as possible while making firm quantitative predictions.
Right.
So once you bring things into the equation that we don't know how to describe in those terms, then scientists sort of are at a loss about what to do. So our goal is to ask the question, is it possible to explain the origin of the universe and why the Big Bang is like it is and what happened before without using any of those categories of explanation? Can we have a purely mechanistic, materialistic explanation for things? And, it might sound very difficult. Maybe the answer is no. But I'm very optimistic that the answer is yes, especially when I think that 100 years ago, we knew nothing correct about cosmology. And now we have this remarkable picture that has been tested many, many different ways and is a very complete story of what happened in the universe in between 1 second after the Big Bang and 14 billion years after the Big Bang. So we'll have to see. I think that, we certainly have good ideas. One of those good ideas might be right. It is absolutely conceivable that someday we'll understand in purely scientific terms what happened not only a fraction of a second after the Big Bang, but at the Big Bang and before.
The mind of God, as it were.
As it were. You get into it. That's the kind of thing that scientists
I know
that's
troubling.
I
know it's troubling, but
it's not troubling. I mean, George Smoot, who won the Nobel Prize just last year, sold a lot of newspapers. In 1992, he was one of the people. He was a lead investigator on NASA's COBE satellite, which was a satellite that measured properties of the background radiation left over from the Big Bang. It used to be that we knew that it was there. Penzias and Wilson won the Nobel Prize in the 70s for discovering it, but it was perfectly smooth. You looked in every direction, and the microwave background radiation, which is what we call it, looked the same in every direction. But we knew that couldn't be precisely right. We knew that there had to be tiny little deviations from place to place, and Smoot was the one who built the instrument that discovered them. And when they were discovered, he said, it's like seeing the face of God. And the word "like" was very important there, but that's the kind of reaction that it invokes when you're faced with these wonderful things about the universe that are helping you understand things that you never could have understood before. It's a natural kind of reaction.
Is our understanding of all of this accelerating at a great rate? It would seem so. As you mentioned, 100 years ago, what did we know compared to today? So given another 100 or 200 or 500 years, the answer may be in that space. Time.
Well, absolutely, yeah. I'm on record myself as predicting that the greatest achievement of the next 50 years in cosmology will be that we will understand what happened at the Big Bang. I have no way of backing up that statement. It's a feeling, and it's an optimistic hope. It's very hard to know what will happen in the future of science. We're very, very bad, historically, at predicting what will happen even 20 years in the future. 50 years ago, we weren't using computers to do science or to do much of anything else. And now, where would we be without computers? 100 years ago, we didn't know about general relativity. We didn't know about nuclear physics. We didn't know what stars were. We knew they were far away and kind of like the sun, but we didn't know where they got their energy from. So there's been a tremendous amount of progress, a mind-boggling amount of progress. On the other hand, progress comes in fits and starts. It's not predictable.
Yes.
So I'm very
is it possible, Doctor, that if we understood what happened at the Big Bang, that we might be able to recreate it?
Many things are possible, including that.
Yes.
I wouldn't bet on that in the next 50 years. But let's emphasize one very, very important thing that even a lot of physicists don't quite appreciate, which is that one of the corollaries, one of the consequences of Einstein's theory of general relativity is that you can make something from nothing, that you can make energy as the universe expands. If you think about it, I was telling you before that the energy of empty space is a constant amount per cubic centimeter, but the number of cubic centimeters is getting bigger as the universe expands. So the idea of creating, within the palm of your hand, an entire universe might seem outlandish and is outlandish, but it doesn't necessarily violate the laws of physics. And people, very respectable people at very respectable institutions, write papers like How to Create a Universe in a Laboratory.
Yes. Well, if it happened once and we come to an understanding of how it occurred, then it's reasonable to speculate.
Gone terribly wrong.
It's reasonable to speculate we might be able to do it again, which, of course, could be catastrophic.
Well, the sad news, maybe, or maybe the happy news, is that even though we don't think it would necessarily violate the laws of physics, we do think that most likely from the outside you wouldn't be able to see it. You'd make a little black hole as far as anyone on the outside is concerned. Inside that black hole, unbeknownst to you, there's a whole other universe, but you can never get there. There might be some rule that says that even if you are able to make universes, you can't talk to whatever's inside.
How sure are we that if we, I know they're working on it at CERN, if we create a black hole, that there will not be enough energy to sustain it, and it will just pop right out of existence very shortly and exist only for a very short time?
We're very sure, actually. And the reason why we're sure is because the kinds of things that happen at particle accelerators. So CERN is one of the two highest energy particle accelerators in the world. The one near Chicago called Fermilab is the highest energy one currently working. CERN is going to break its record next year, and they're going to collide protons with each other at tremendous energies, and you might worry that they make black holes and the black holes swallow up the Earth and so forth. That's a reasonable worry to have until you realize that similar collisions happen in outer space all the time. cosmic rays are nothing other than very, very high energy protons, and they bump into each other. And nothing disastrous has happened. If these black holes did spiral out of control, we would have known it a long time ago.
Uh-huh.
So, I mean, the truth is that even though by particle physics standards, there's a lot of energy that we're putting into these particles,
Doctor, I've got to cut you off there. I'm sorry. We've got a break. We'll be right back with Dr. Carroll. What if we could travel out to the end of what we know as the edge of the universe, whatever it is, 14 and a half, 15 billion years out, light years out? We could get out there, actually get out that far. What would we find beyond it? Anything? Nothing? Would we return to the point that we started from? Would there be a big wall there? Or just an eternal nothing beyond, into which everything will continue to expand at an ever-increasing speed? A good question, one for Dr. Carroll in a moment. Well, all right, my guest is Dr. Sean Carroll, and the question, I guess, is what are we expanding into, Doctor?
That one we think we know, and the answer is we're not expanding into anything.
Oh.
It is that when we say things like distant galaxies are moving away from us, what we really mean is that the space in between us and that galaxy is stretching. There's becoming more and more space. So it is completely possible, again, we don't know for sure, but one of the absolutely plausible models of the universe says that what we see just continues forever and ever without ever reaching anything else. We're not expanding into anything. It's the universe we're talking about. It's all that there is. But the amount of space is growing just because Einstein says that that's what it's going to do.
So as we expand, that offers new real estate. In other words, it's not new real estate until we expand into it.
We're not expanding into it, but there is more and more stuff out there. So what appears to us is that the local amount of stuff is relatively going down. You know, the galaxy is moving away from us. It's not an optimistic scenario because even though there's more light years to the universe, there's the same number of galaxies, and they're just moving further and further away.
Yeah, so I've heard it said we will eventually not see stars in the sky anymore. Everything will move away from us, and it'll be a cold, lonely sort of death.
Yeah, that's very possible. I mean, even though we don't know what happened before the Big Bang, we also don't know what will happen in the very far future. But extrapolating from what we do know, stars that burn use up their nuclear fuel, and there's only a finite amount of that per star. So distant galaxies move away. The stars within our galaxy use up their fuel. Some of them explode. Some of them just fizzle out. You'll make some more stars in the future, but eventually you're going to run out of stuff to make them from, and you're left with a very dark, cold universe.
That's a dismal future.
Well, it may or may not be a dismal future, but that's not our job as scientists to judge that. We have to figure out what the universe is giving us.
Uh-huh.
Now, to be more optimistic maybe, it could be that out of this apparently dead universe, billions and billions of years in the future, there will be very unlikely but eventually inevitable events by which you make baby universes, by which you make new universes. So it's possible that even though our universe will give up the ghost after some time, other universes will continue on the fight.
Well, I'm worried about our planet right now, essentially giving up the ghost. We have so much going on right now, which is so worrisome, and I know that this is not what you study, but with the current reports coming out on the climate, with the bees disappearing, with all of the problems we seem to have on Earth, weather will be around long enough to make the discoveries that you hope to make in the next X number of hundreds of years. I'm just very concerned that we'll make it that far.
Yeah, I think it's right to be concerned. I mean, we can talk about these fun things with the energy density of empty space and the Big Bang and baby universes, but the resources that we have here on Earth, many of them are very, very finite. And we're using them up, and we're using them up in a particularly sloppy way. And I'm not a climate scientist, for instance, so I can't tell you with any confidence how the different cycles in our atmosphere work to block out solar rays or keep things in and so forth. But I know, just by looking at the data, that we're dumping gases into our atmosphere at a rate that the atmosphere has never had to experience before.
Right.
And it just stands to reason that if you take a sledgehammer to something as complicated and interconnected as our ecosystem, you're going to break something. Now, people who know more about this than I do go into details about how things will break and what the breaking will look like. But the first thing that we should think about doing is just being a little bit more gentle about how we treat the planet.
Is it possible or even probable, Doctor, that life is common? Life perhaps progresses along a similar line to ours, and then at some point almost always extinguishes itself and is some sort of giant cyclical type of thing where we're here for a very short period of time. You get to a certain scientific industrial point and you extinguish yourself.
It's certainly possible. It's I'm absolutely incapable, as is everyone else who I've ever met and you've ever met on Earth, of saying whether it's probable or not. We just don't have that kind of data. But it is what happens, obviously, as a civilization becomes more technologically advanced, is that the powers that they can wield become more and more able to have a big effect on whatever planet that they live on. And if their powers outstrip their wisdom and their foresight, then they can get into trouble. It's certainly not at all implausible that in a few hundred years we could wreck the planet once and for all. That's not implausible. Whether or not we will and whether or not that often happens is completely up in the air. Like I said before, we're in this unprecedented part of history where we are changing and learning and evolving what we can do so quickly that we have no guidance from the past on how this is going to play itself out.
Mm-hmm. You mentioned something in here called quantum gravity, and I barely understand beyond, gravity comes from mass, but quantum gravity, I'm still, struggling with the whole quantum concept itself. Quantum gravity, what is that?
Well, this is one of the great unanswered questions in theoretical physics. This is one of the great frontiers that people are devoting themselves to. Quantum mechanics and general relativity are the two wonderful successes of 20th century physics, but sadly they're incompatible with each other. Einstein understood gravity. He realized that it was not a force acting at a distance, like Isaac Newton said. Instead, it was the curvature of space and time. And then a bunch of people, Einstein included, but many other people, realized that Newton was also wrong about sort of the basic workings of things. When he said F equals ma and action equals minus reaction, there was a fundamental... He was making an approximation, essentially, where he thought he was describing the world exactly, but the real world is much more complicated and subtle than that. And quantum mechanics is the theory that explains how things work when you look at them sufficiently closely that the approximation breaks down. In quantum mechanics, according to Isaac Newton, if you have a ball, then it has a position and it has a velocity. In quantum mechanics, that ball doesn't have a position or a velocity. There's no such thing. There is some function spread throughout the universe that gives you the answer to the question, what are you likely to observe its position to be when you look?
Right.
Quantum mechanics tells us that the number of things we can observe is enormously smaller than what really exists. We can observe certain features of things, but we only get certain answers. We'll never sort of capture the true reality of it in any one observation. And now that's true. This is part of how we understand the world. I mean, if it wasn't for that, then lasers and transistors and all sorts of interesting things wouldn't work. Also, we don't know how to fit gravity into that framework. Even though Einstein's theory of general relativity overthrew Newton's law of gravity, it's still at heart a very Newtonian theory, a very clockwork universe theory. If you know in principle everything there is to know about space-time, then you can predict in principle everything that we'll ever do. And no one thinks that that's the right answer. No one thinks that's the final picture. Someday we will have to learn to reconcile these two great triumphs with each other. And when we do, we will call that quantum gravity. We have some good ideas along that direction, but we don't yet understand it.
Would gravity be a force that would move from one universe to another?
Depends on what you mean by another universe. We're, again, in a realm here where the language hasn't quite caught up with
the notion of parallel universes, for example.
Yeah, so there's different ways to have other universes. You can have other we often talk about other universes, but we just mean parts of our universe that are very far away where conditions are very different. That cosmologists often talk that way. It's also possible that there are extra dimensions of space that we don't have access to quite yet. They could either be very small or very highly curved, so we can't notice them. And then there could be a whole other universe sort of literally next door, a tiny fraction of a centimeter away from us, that we haven't noticed because it's a different location in the extra dimension. And this is the word dimension here also is fraught with meanings that it should necessarily have. We really mean just a physical dimension of space, just like up and down is a dimension of space, but a new one that we haven't seen yet. So in that case, it is very much true that gravity would be able to influence things from one universe to the next. And one of the constraints on types of parallel universes is that we haven't noticed any such gravity yet. Everything that we have observed the universe to be doing seems to make sense within the hypothesis that the things causing gravity are here in our universe. But this is something we need to keep an open mind about. We know a lot about the stuff that is in our universe, but there is still room for surprises.
Well, we have this expansion going on, and we attribute it to some sort of energy.
Yes, dark energy, we call it.
Dark energy, which is sort of a theory. In other words, we haven't actually measured dark energy yet, or
we haven't detected it directly.
Exactly.
That's right.
So
that's right. So we keep an open mind, and this is one of the things that I do for a living: is keep an open mind about why is the universe accelerating? Could it be because we don't understand gravity, for example? Could it be because there are influences from parallel universes, if you want to call them that, elsewhere in some extra dimension? And, we write papers about this, filled with equations, and usually at the end of the papers they say, well, this idea doesn't quite work. We haven't had any ideas along these lines that makes all of our confusions clear up and snap together. So it is, on the one hand, very much an open possibility. On the other hand, nothing especially promising along those lines has yet been suggested.
Okay. String theory. String theory, is it going to, are we going to confirm string theory with CERN? Is that a possibility?
That's a possibility, but that's one of those ultra-long shots. I wouldn't place any bets on that at even money. The great thing about turning on a new particle accelerator or any other experiment is that you don't know ahead of time what you will see. We have some expectations. We have some ways that we could learn about string theory at CERN if everything breaks right our way. But it would be, actually, it's much more likely that we'll discover new and amazing things when CERN turns on its new accelerator, but none of them will be directly telling us about string theory. And basically, that makes sense. The reason why it makes sense is because string theory is a theory of quantum gravity, and gravity is a very weak force. You don't feel gravity until you have a whole planet full of stuff exerting its gravitational pull on you. So we can do experiments with a single electron and detect its electrical field very, very easily. But to detect the gravitational field of a single electron is absolutely hopeless, just because it's so small. So that's the problem, that we want to reconcile gravity with what we know about electrons and quantum mechanics, but the data are not forthcoming because gravity is so weak.
Doctor, how big a screw-up was it that we did not go ahead and build the superconducting super collider?
It was a super screw-up. It was a giant, enormous screw-up. And I think that even the people who many of the people, including, for example, Bill Clinton, who was president when it was canceled, admitted that it was a mistake. So this accelerator that is being built at CERN, that we're all very excited about, is much later and not as energetic as the superconducting supercollider would have been. So we would know the answer to many questions now that we don't know, and even CERN will not tell us. It was a short-sighted decision. It was, it was a different time in the 1990s when the budget deficit looked like it would never go away until this brief shining moment around the year 2000 when we had a surplus. But everything's more expensive now, so to do something like that would be even more costly. And the thing about basic research, which is what that is that ultimately it always pays off. You don't know how, but it's part of pushing back the frontiers of what we understand, and the new knowledge that you get, either in discovering things at your experiment or just discovering how to build your experiment, pays off in unexpected ways.
In terms of magnitude that we might be able to understand, how much bigger and better and more results would the superconductive supercollider possibly have yielded?
Well, it's very hard to say in terms of results because you don't know what the results are going to be. The best way to put it is that there's one particle that everyone is looking for called the Higgs boson. There's many, many particles that everyone is looking for and the hopes that are there, but the Higgs boson is the thing that almost everyone is convinced that either it exists or something like it exists. We can sort of infer its effects, but we can't quite put our finger on it yet. And the accelerator at CERN is very likely to find it, but it might not. The superconducting supercollider would have found it, one way or there's just no question. That would have found it, and we would have moved on and be discovering new things beyond that. So it's, like training for a marathon by running 10 miles all the time. And, maybe you'll be able to do the 20-some miles when you get to the day. Maybe you won't, instead of training by doing more than that. So,
all right, if we had discovered that particle, what might that have explained?
Well, the Higgs particle, according to our current understanding, is the thing that gives elementary particles their mass. So the photon, for example, has zero mass. The electron and the quarks have some non-zero mass. Why is that? The Higgs particle is the thing that makes the difference. The Higgs particle is the thing that basically gives a stickiness to space itself and slows down particles moving through it. So you imagine that as far as the photon is concerned, it's like moving through empty space, but the electron is like moving through molasses. It's slowed down by the medium through which it moves, and that medium is the Higgs particle. So it's really a fundamental building block. It's not just another particle amongst the several dozens. It's a special particle. It's doing something that is really, really important for understanding about how nature works. And it's a target. It's something that we knew would have been there. Either, let's put it this way, either it would have been there, or something even more new and exciting would have had to be there to do the job that we know the Higgs particle is doing, because we know the electron has a mass. Something is doing this job. And we would have answered that mystery at the superconducting supercollider. We're hopeful about answering that mystery at CERN several years later, but it's not at all a sure thing.
And there's no way to project what practical application might come from an understanding of whatever it is that particle is.
No, there's no way to project. It's possible that for the foreseeable future you would not have had any practical application. I certainly can't think of a way to have a practical application, but no one understood the practical application of the electron when it was discovered either. So it's not the reason why we do this. The reason why an honest particle physicist will say, why should we spend $1 billion building your accelerator? They're going to say, well, because we want to know the answer, because we're curious, because we want to discover things. So that's the real reason to do it. And if that's not worth the money, then don't do it. But a lot of us think it is worth the money when you say that that's an amount of money spent over a period of many, many years, and we learn a lot of things along the way.
Well, I suppose if I were heading a committee and I were to ask you, look, if we discover this, what are the possible applications? I'd be looking for some sort of concrete answer to justify the expense, right?
You could be. Or, I mean, what are the possible applications of discovering new planets that look like Earth? There's not going to be anything within the next 50 years that makes us build a better television or better internet because we discovered an Earth-like planet.
Well, maybe a new home, if we need one, might be one possible answer. Doctor, hold on, we're at the top of the hour. Dr. Sean Carroll, bottom of the hour. Dr. Sean Carroll is my guest, and we're off into space and time, big time. I'm Art Bell. My guest is Dr. Sean Carroll, and we're talking about things that, mark our beginning, really. The beginning of everything, which we still don't fully understand by a large measure. There's something called the arrow of time, apparently. In just a moment, we'll ask about it. Doctor, the arrow of time, I guess I'm going to ask you about the origin of it, but I don't even know what it is, so I'll ask about that first.
Well, it's just the fact that the past is different from the future. You remember the past, and you don't remember the future, for one thing.
That's right.
We have this thing called entropy that is telling us, for some physical arrangement of stuff, how orderly or disorderly it is. And one of the most important laws in all of physics, the second law of thermodynamics, says that in a closed system, the entropy always goes up. If you leave something to its own devices, it will become more and more disorderly. And this is why when you put an ice cube in water, it will melt and become the same temperature as the water. But if you put a glass of water out there, it will never spontaneously form an ice cube.
Right.
Certain things happen in one direction of time, but not in the other one. Now, in a sense, every time you put that ice cube in a glass of water, you're doing observational cosmology. You're learning something deep about the entire universe. Because the ultimate reason why entropy keeps going up is because near the Big Bang it was incredibly tiny. And that's a mystery we don't quite yet know the answer to.
Is it possible that with enough energy we can go the other way?
Well, what you can do is you can certainly arrange things very, very delicately so that things appear to go the other way. So if you like, it's sort of like if you are playing billiards and you rack up the pool balls with your triangle and you just sort of smack them, then almost inevitably the balls are going to scatter across the table. But you would have to be a super expert pool player to have the balls scattered across the table and in one shot hit them so precisely that they all go back to a perfect triangle as if they had just been racked. That's the equivalent of what you would have to do. That's not breaking any laws of physics to do that. You just have to be the world's best pool player times a million. So we could do that in some very localized circumstance, but only at the cost of increasing the entropy of the rest of the universe. So for the universe as a whole, the entropy is always going up, even if we mess around with some tiny little bit of it.
So I'm not sure what you just said. I guess you're saying in some special local circumstance, it might be possible to essentially travel back in time?
No, it's that the rule is that in a closed system, entropy always goes up.
Right.
However, there's plenty of not closed systems. You can arrange systems to be influenced by the outside world. You can make ice cubes. Even though the whole world wants to settle down to one temperature, we have the sun continually pumping us energy in here, and we can use that energy to do things here on Earth. So we can't make time go backwards. We can temporarily, in a very, very, very limited way, make the entropy decrease or appear to decrease. But memory is something that requires entropy increase. The fact that we remember the past and not the future is due to the fact that we are increasing the entropy as we go to the future. So you would have to make something as complicated as a human being and have its entropy decrease spontaneously if you wanted to somehow get the perception that time was going backward.
What about forward? What if you wanted to increase the speed and actually go forward in time?
Oh, that's easy. That's one of the fun things about time, is that it is just a technology problem, as we put it before, to go into the future faster than you normally do. Einstein taught us how to do this. I mean, there's the sort of cheap and easy way to do it, which is to go into suspended animation, but that doesn't quite count. The more interesting way to do it is to move near the speed of light. If you move around, even just around in circles, at a speed close to the speed of light, then when you're done and you stop and you talk to your friends, you will have experienced less time to have passed than they will. The problem is you can't go back. So if you move at the speed of light for what feels to you like a week, and you do it so effectively that you come back and everyone else has seen 100 years go by,
you're permanently ahead.
You're there. You're stuck. You can't come back. That's right. As far as we know. This is what the laws of physics, as we currently understand them, say. This is something where we have to admit the boundaries of what we understand and what we don't. We don't understand the laws of physics well enough to say that there aren't loopholes in that. So that's another thing that we're still thinking about. Is it possible to warp space and time so dramatically that you could go back and report from what you discovered in the future?
Doctor, when I was a child, I was told with some confidence that the universe was expanding, however, not at a faster rate. Moreover, at some point, like a rubber band, it would get out there as far as it could go and would snap back, and there would be a collapse. Now, is that whole idea collapsing?
That idea is much less likely now. There was never a point that any respectable cosmologist would have told you that the data are telling us the universe will eventually recollapse. A lot of people thought that was a very natural way for the universe to behave, including Einstein. Einstein basically was of the opinion that someday the universe would recollapse. There's a certain nice symmetry to that. The universe expands, it stops, and it recollapses. That's kind of pretty and compact and contained. But the observations never told us that was happening. That was always an open question. And now we've made the observations, and the observations are telling us that not only is it not collapsing, it's expanding faster and faster. This drives home the fact that the past is very different from the future. The past, the universe was not only was the entropy small, everything was clumped together, very hot and dense. And in the future, everything seems to be like it's going to be spread out and very cold and dilute. We were not as good at predicting the future as we are at observing the past, but our simplest and most compelling theories right now are saying that the smart money is on a universe that expands forever.
How can we prove, or are we going to be able to prove, the existence of this energy, pin it down, perhaps even use it, this energy causing this ever-expanding universe?
Well, that's a very good question. A lot of brain power and technology right now within professional cosmology is being devoted to probing this idea of the dark energy. What is it like? Is it absolutely constant, or does it change ever so slightly from place to place and from time to time? Can we someday detect it directly?
Yes.
Can we sort of bounce photons off it somehow?
Yeah.
We don't know. We're very much in the early days of this game, so we're coming up with new ideas, and I can say that it is absolutely possible that once we're done coming up with these ideas, we'll realize that there is no way to directly detect it, that there's no way to put it to any good use or anything like that, that it's really just an inherent feature of space-time itself that we're just stuck with. On the other hand, there's also other possibilities. There's more exciting possibilities that it could have an effect on how light travels to us from distant galaxies, so we could help detect it directly that way, that it's somehow there's a field associated with this energy that gives us a fifth force to nature in addition to the forces that we know, and we're looking for evidence for that fifth force. So it's a very exciting time for exactly that reason. We've discovered this new thing, and we're playing with it. We're trying to figure out what it's going to be like once we finally understand it.
Doctor, we've sent out a couple of deep space probes, and it's my sort of recollection that there is an acceleration involved with them that we did not expect, but we have measured. Is that true?
That's right. There's something called, or at least it seems to be right. This is a tricky thing, but there's something called the Pioneer anomaly.
Right.
And it's an amazing fact because we sort of got lucky. NASA in the 1970s was, in some sense, more ambitious than they are now. They were sending a lot of probes to the outer solar system. There were 2 Pioneer satellites, and there were also 2 Voyager satellites.
Mm-hmm.
And the reason why there's a Pioneer anomaly and not a Voyager anomaly is the Pioneer satellites steered themselves just using gyroscopes. So the trajectory of the spacecraft itself is just purely moving through the solar system unimpeded, but you can sort of tilt it and twist it around its trajectory by altering the gyroscopes. And that makes you able to measure where it is and where it should be to incredibly good precision. On the other hand, the Voyager satellites have little rockets on them, and they orient themselves by firing their rockets ever so slightly, which does help you move the satellite, but it also deflects it from its trajectory, which means that you're not as good at measuring it where it should be.
Right.
So the 2 Pioneer satellites, one we don't have as good data on, but the other one we have very, very good data. We know where it is and where it should be, and it seems as if it is feeling a force. It is not quite moving through the outer solar system in exactly the way it should be. It's being pulled toward the sun just ever so slightly more than we think it should be. Now, it may be that there's something deep going on. It may be that we don't understand gravity, that there's some real new phenomenon in nature that is explaining this.
Well, I was going to ask if it could be this same dark energy we were just talking about.
Well, no one knows. I mean, that's a natural question to ask. It's a perfectly respectable thing to say, maybe that's true. But then you want to go from that to say, okay, how could it be true? How can we write down a model? How can we invent a new theory that would simultaneously explain the acceleration of the universe that is purportedly due to the dark energy and explain the Pioneer anomaly? And my impression, and this is what I do for a living, is that no one has written down such a model that works. And it's something that certainly people would love to do. I mean, there's a lot of brain power that has been devoted to trying to do things like that, yet without any success. That's not to say that tomorrow morning someone will not do it, but we don't have any good ideas along those lines yet.
I have a hard time imagining an energy like this dark energy that you speak about that we're unable to measure. That I mean, every other kind of energy that we've come up against, we've always been able to quantify and measure in some way or another. And yet here we have an energy that is there and is virtually pushing the universe apart, and we can't get our hands on it.
Well, we haven't measured it yet, but the reason why we think it's there is because we think that we've measured its gravitational effect.
Sure.
Right? Now, you're willing to believe that we've discovered the third planet around Gliese 581. And why are you willing to believe that? Because we've measured its gravitational effect. It's making its host star wobble a little bit. And we infer from that wobble that there's a planet moving around the star, even though we don't see the planet. It's exactly the same chain of reasoning that leads us to believe in dark energy. We measure the motions of galaxies throughout the universe, and we infer from their motions that there's a gravitational field caused by a constant amount of energy spread throughout the universe, and we call it dark energy. And then we try to test that hypothesis. That's a hypothesis that was measured in a certain that was invented to explain a certain phenomenon. Now we use it to predict other things, and so far it has made predictions, and the predictions have come out correct. That's not to say that that will continue to happen. We could always discover something new and exciting that would give us more insight into what's going on. But either dark energy is there or something even more exciting is going on. It's not that we've just made a mistake.
Okay. Yeah, let's come back to the third planet for a moment, this new planet we've discovered. I can understand how we discovered the planet because it moves in front of the sun, okay, and we see a little perturbation. We say, okay, that's a planet. But it seems to me we've concluded an awful lot in this article I read. I can understand how we would conclude, for example, the temperature on that planet because of its distance from the sun. Okay, I've got that one. How do we conclude, though, that the planet would have an atmosphere, that it would have water, and on and on? How do we conclude these other things?
Well, I think you're exactly right to perceive that those are not even really conclusions. Those are reasonable
guesses.
Guesses is perfectly fair. What we know is that given the distance of that planet from its star and given its mass, it would be perfectly reasonable for it to have water and have an atmosphere. There's absolutely no direct evidence that it does have water and an atmosphere. We're very far away from being able to conclude that.
Oh. Okay. Well, that's quite a change. I mean, this article, it seems to suggest that they are there. The atmosphere is there. The water is there. So that's sort of speculation.
That's right. If you read an article that said that was an overly enthusiastic journalist. What we know is that there's a planet that is in the habitable zone, and it has a surface gravity that is comparable to that of Earth. So it's probably a rocky planet. It's not going to be a gas giant like Jupiter or Saturn. It's going to be a rocky planet. It has a temperature that is, room temperature-like on a typical day. And according to everything we know about planets, which is not that much compared to how much we should be able to eventually know about planets, but according to what we know now, those kinds of planets are very likely to have atmospheres and perhaps even water. But that's just, an extrapolation. That is not something that we've observed yet. That would be very, very hard to observe because this is a very dim, tiny planet very far away.
And then there is no, assuming, if you make the assumption that there's atmosphere and that there's water, you cannot extrapolate from that and say, all right, then there's definitely going to be organisms at a minimum. Can you?
No, certainly not. That would, here is a possible future for the next century. The possible future is that our increase in understanding of how biology and the origin of life works will be as spectacular over the next 100 years as our increase in knowledge about how the universe works was over the last 100 years. Right now, we're really at the very beginning of being able to understand those things. There's some provocative experiments. There's the famous Miller-Urey experiment where they zapped some electricity into a jar full of chemicals, and they got amino acids out. So that's good. That's promising. But to go from there to life is a long way, and we don't know how it works.
So I was about to ask that. In other words, could we create a soup, and then can we actually get to life? And your answer is no, we can't get to life. Amino acids, but not life.
At the current state of technology, that's exactly right. We can make amino acids, and we cannot make life. Now, the Earth, of course, had many billions of years to work on this before it happened, or at least a couple billion years. So maybe it's not surprising that over the course of a few weeks in a jar, we were not able to do it. But how often it happens, what the conditions are for it to happen, the different kinds of ways that it could happen, are things that we don't know any of that yet. I predict that 100 years from now we will know it, but I'm not going to tell you what the answers are because I don't know.
Yes. When we get amino acids, how far are we from life?
Well, I think that that's part of what we don't know the answer to. We're very. It's easy to make a list of steps. You go from amino acids to proteins, from proteins to DNA, from DNA to cells, etc. But how difficult it is to take every one of those steps is something that we are very clueless about right now.
We really are clueless still about a lot of things, aren't we?
There's many more things that we have yet to understand than we've already figured out. That's right. We figured out a lot, and there's even more that we haven't.
I hope we have the time to figure out a whole lot more, because I sure would like to know a lot more, and obviously you would too. That's the business you're in.
That's right. I'm lucky enough to have this as my job.
It really is a lucky job. Your job is to sort of sit and think about possibilities, what might have happened and what might yet happen. Is that fair?
drink coffee, write down equations, and think about possibilities. That's right.
What a job. All right, when we get back, what I'd like to do is allow the audience to ask you questions, perhaps ones that I've not thought of yet, and it's always a lot of fun. So if you're ready for that, that's what's coming next. All right, Dr. Sean Carroll is my guest, and indeed he'll be up for your questions next. So if you think along these same lines, these lines of, I don't know, where did we come from? How did we get here? And where are we going? Then we're all set for you next. I am indeed a creature of the night, and this night, so is Dr. Sean Carroll. And he's here to answer your questions this hour. And many, many questions should have been generated. I'm sure you have them. The board is loaded, so in a moment, we'll get to you. Dr. Carroll, as we go along, I get questions by computer as well as people phoning in, and I kind of like this one from Russ in San Mateo, California. He says, universal expansion, ? If the universe continues to expand, with galaxies receding from each other, how is it we do not find ourselves and our own constituent atoms also moving further away from each other?
There's a very good question. Many of the students in my general relativity classes always get annoyed at exactly this question because it's a tricky one. But the answer is that things that are held together by their sort of mutual forces don't expand along with the universe. Huh. The closest that I can come to a good explanation of this is to think about the universe as a rubber sheet that is being pulled from all the edges, so the rubber sheet is getting bigger and bigger. And individual galaxies or planets or solar systems on the rubber sheet are sort of like pennies or other coins that you scattered on the sheet. They move apart from each other, but the individual pennies don't become bigger. The space underneath them is sort of changing, but the forces within inside the penny are much bigger than that, and they're going to hold it together. Likewise, the gravitational forces that hold our galaxy together or our planet together, or the electrochemical forces that hold us together, are completely unperturbed by the general expansion of the universe, which is a very, very negligible thing.
Okay. All right. Sean in upstate New York on a wildcard line, you're on with Dr. Carroll.
Good morning. Thanks for taking my call.
Sure.
Regarding the new planet that was discovered, it's circling, or it's orbiting, rather, a red dwarf star.
That's right.
And are not red dwarfs very much colder than our star, for example?
Well, I would say they're a little bit colder, and this planet is also substantially closer to its host star.
I see. I have another question. Is there actually such a thing as antimatter?
Absolutely. We make antimatter all the time in our laboratories.
You do?
Oh, yeah.
And I take it doesn't last.
No, it generally doesn't last. In fact, that's one of the tricks. So you want to make antimatter and you want to do things with it. So you want to keep it from touching anything else. If you make an anti-electron and it touches a regular electron, then it annihilates into a very high-energy photon, a very high-energy gamma ray. So you want to trap it and keep it far away from everything else, and we've sort of developed techniques to do that. So we've mentioned before the particle accelerator at CERN in Geneva. That's going to collide protons with other protons. But the current record holder at Fermilab outside Chicago collides protons with antiprotons. And that's something that we've learned how to do, and people are even now making anti-atoms. They're making anti-hydrogen.
Can we make enough antimatter to eventually, I hate to use the word explosion, but I take it when you collide a large amount of antimatter with matter, that's what you get.
That's right, but that would be a very inefficient way of making an explosion. The amount of energy you would need to make to create all this antimatter in the first place, you might as well just put that to work making an explosion.
Okay, Lauren in Santa Monica, California, your turn with Dr. Carroll.
Hi, Dr. Carroll and Art. How you doing?
Fine.
I've got a question regarding getting outside the paradigm of traveling at the speed of light with mass, since there's so many complications with that. And what about traveling at the speed of light with just information, either on a radio wave or a light wave, to Gliese or maybe the supermassive black hole at the center of the Milky Way, and assuming that if those civilizations are billions of years ahead of us, that they've got some kind of technology to perhaps decode the human genome and perhaps consciousness, if we can map that eventually as well.
Mm-hmm.
Well, we do, in fact, of course, transmit information at the speed of light all the time. That's how you're hearing this on the radio. But what you're now suggesting is transmitting enough information to reconstruct an actual organism. And that's something where that is very difficult to imagine that that's possible even in principle, much less in practice, because it's not just a matter of a list of ones and zeros telling you what atoms we're made of. You need to put every single atom and every single electron inside you or me delicately into its correct position. And we don't even know how to measure that, how to find out where every single atom inside you or me is located.
No, I agree with you or me, but sometimes we get this egocentric thing that we have to send ourselves at the speed of light to another planet or another solar system. But in terms of the unrelenting drive to continue the human race, if we just send our genome and a certain amount of information to a more advanced civilization, couldn't they, in fact, at least decode it with their technology and at least create a being similar to us, in a way, one of our children?
Well, we could, something like that is much more feasible, yes. However, this is a relative concept, much more feasible. It's still asking quite a lot. We would first need to teach them enough of a language so that we could communicate, and we would have to presume that they're interested in creating one of us. And then what they get out of that is, of course, a little, let's be very, very speculative, why not? The most they could get out of that is a little human baby, which would know nothing about life here on Earth. They would not be able to tell from the human genome what kind of atmosphere and food and conditions would keep that baby alive, et cetera, et cetera. It would be a fascinating scientific bonanza for them, but what they'd be able to do with it is very unclear.
It also might be very dangerous for us.
Well, I think that's a very real fact. I mean, in general, in the history of the Earth, when two groups of people have come together into contact and one of them is much more powerful than the other one, the result has not been pretty.
No.
And it's this tension, this push and pull when we think about extraterrestrial civilizations. Of course we want to find them because it's amazingly fascinating and endlessly intriguing. On the other hand, we don't want to be rubbed out.
Right.
And something that is even 100 years technologically ahead of us, much less a billion years, would be very hard for us to deal with. So,
for that very reason, Doctor, would you object to the idea of sending a very, very strong signal toward an area of space that we considered suspiciously likely to have life?
I don't know. I wouldn't necessarily object to it because it is endlessly fascinating. And also I suspect that if other civilizations are advanced enough, we've already given the game away. We've been beaming weak signals into space for years now. So if they want to find us, I bet that they will. And I think that the single biggest piece of evidence against the fact that they exist anywhere near us is they haven't found us yet, as far as we can tell. But these are all highly speculative. I'm willing to be proven wrong. My opinions about these are not highly developed, and I think that that's why it's great that we're making discoveries along this way. Once we continue to understand better and better how life works and how frequent it is and how planets work and how many of them there are, we'll be able to have a much better idea of the answers to these questions.
Well, here we are with this planet we just discovered. I suppose if we discover in some way or another that there is indeed life on a planet, just like this one that we just discovered, then the whole ball game radically changes, and the numbers suddenly become very meaningful, tilted toward life, right?
Well, yeah, it depends on the circumstances under which we find it, but and of course, it's hard to extrapolate from one of anything, but one is a whole lot more than zero, and it would teach us a tremendous amount to discover anything like that. And
is there any experiment, Doctor, that we can perform with the knowledge we now have of this planet we just discovered that would be that would give us some sort of evidence that life is likely there?
We don't have any way right now of doing something that would tell us whether or not there's even an atmosphere on this planet, much less life. That's not to say we won't be able to think of it, but right now it's straining the limits of what we can do just to detect its gravitational force. But to figure out its composition, what it's made of, what its atmosphere is like, much less whether there's life there, is something we don't have any idea how to do yet right now.
Got it. Patricia in San Francisco, you're on with Dr. Carroll.
What
Hi.
an honor to speak with you, Art.
Thank you.
My question has to do with the Brookhaven Heavy Ion Collider. It came online in 1999, and its purpose, as I understand it, was to create one of them, miniature black holes. Just out of curiosity, I checked when the ice sheet started melting, and that was the year 2000. And now I've heard that the solar system is heating up, and no one knows why. The thing about when you put something under pressure, it increases heat. And I'm wondering if there's some way of figuring out, testing, whether or not the black holes have decayed, or if in tandem for the brief moments that they are in existence are having an effect on our environment.
Sure. I mean, I think you're putting you have two very interesting facts here, but I don't think they're really connected. I'm not sure what the thing you heard about the solar system heating up is.
We know Mars is heating, I believe.
Well, all the planets have cycles of their temperature. I don't even know what it means to say that the solar system is heating up. I know what it means to say the Earth is heating up, which seems to be true. But I'm very, very sure that Brookhaven is not to blame.
Well, the other thing is that the earthquakes in the Western Pacific, which have compacted the crust, and our planet is also sped up ever so slightly. That also kind of is a little red flag warning bell. It's like the Earth is compacting, speeding up, and heating up. And that just leads me from basic physics to think, there's something at work here, and I wonder what it might be.
Well, what you have to realize is that before Brookhaven turned on, this is another particle accelerator, but instead of smashing together two individual protons, they're smashing together the nuclei of heavy elements like lead and gold, so huge collections of many protons and neutrons. It was very reasonable to speculate that maybe we'd get lucky and have something truly spectacular come out of that, like making a little miniature black hole that then decayed away. But the places at the particle accelerator where the two different ions are colliding are some of the most carefully observed places on the planet Earth. We have very many very precise detectors located exactly there, and they're measuring exactly what happens when these ions collide. And we're fascinated by what happens, but making black holes is not one of them. And you could very easily stand right next to one of those detectors, and you might be able to slightly warm your hands next to it, just as you would by your oven. But it's the millions and millions of tons of carbon dioxide that we are putting in the atmosphere that are affecting the overall temperature of the Earth. It's not the occasional collisions of gold nuclei at Brookhaven.
Okay. Mike in Ohio, you're on with Dr. Sean Carroll. Hi.
Good evening, Dr. Carroll.
Hi.
Gentlemen, since gravity seems to be the result of mass, I don't feel consciousness is a companion to gravity like the chicken and the egg. I feel consciousness is, say, quantum energy that's an effect of the original causation. So, Dr. Carroll, could consciousness and this dark energy be intertwined like DNA, where one's, say, a carrier wave for the other kind of quantum consciousness?
Well, I think that on the one hand, consciousness is one of the things we understand the least. And I'm not going to pretend that we know how it works. On the other hand, dark energy is something we actually, if anything, we understand dark energy better than we understand consciousness. And one of the things about it is that given all of the experiments that we've ever done in physics, we never noticed the dark energy until in 1998 we did observations of very distant supernovae in other galaxies. So whatever the dark energy is doing, it's not interacting with you and me and the stuff we're made of in any appreciable way. It has a gravitational effect that builds up over millions and millions of light years so that we can detect its very faint push on distant galaxies. But here on Earth, in the motions of the things zooming around in our brains, there's no appreciable impact of dark energy. So I think that thinking about consciousness and trying to figure out what it is fascinating, and one of the things that we're going to be learning a million things about in years to come. I've sat on some great committees. Committees are generally not great things, but I've sat on some committees for graduate students defending their PhD theses that were working on the mathematical physics of neurobiology, and the kinds of things that are being done right now would knock your socks off in what we are able to understand. But it's still just, getting our feet damp at the edges of a very enormous ocean. It's a long way to go. So I would stay tuned to the kinds of things that we're going to be learning about that. But I would not bet on dark energy being part of it.
All right. Charlie in Florida, you're on with Dr. Carroll.
Good morning, Art. Good morning, Dr. Carroll.
Good morning.
Hi.
I'm just a mortal, and I'm trying to follow the Big Bang situation with your explanation here tonight. And what I'm gathering, to us mortals, a bang is the sound made by a big explosion, therefore implying that there was some sort of explosion which started everything. But what you're saying is that it wasn't really an explosion because there's no point of explosion from which everything's radiating, but something happened and we don't know what it was that started everything. Wouldn't it be more accurate to call it the giant Ooga Booga?
Yeah, the moment itself, t equals 0, as a mathematician would say, the beginning of time, is not something we claim to understand. The name, the Big Bang, was coined by Sir Fred Hoyle, an astrophysicist in the 1950s who didn't believe in the Big Bang. He was basically making fun of it because it's kind of a silly name, the Big Bang. You should be able to be a little bit more dignified when you come up with your best theory about the origin of the universe. So we're working on that. There are things we know about it. It's not that we don't know anything. We know that it was not an explosion as in some bomb was sitting there ticking in a pre-existing space-time. But we don't know whether or not there was some space and time before the Big Bang. We don't know whether we're a baby universe or a unique universe. Do we have other brother and sister universes elsewhere out there? We don't know what the far future will hold either. So we're doing our best. We're speculating at the edges of what we currently understand, and we're very interested in new data, new observations that are coming in. So I'm optimistic about understanding the Big Bang, but I'm happy to admit that we're not there yet.
Doctor, in working backwards, it's not possible then to roughly determine a point of origin?
Well, we know when exactly our information gives out. So we know that the universe is about 14 billion years after the Big Bang, and we know what it was doing 1 second after the Big Bang. But we don't know what it was doing half a second after the Big Bang or a tenth of a second, etc. So in terms of time, there's a moment when we have our earliest information about, and it seems to fit the theory.
Okay, well, I was thinking more of an origin, though. I mean, if you move everything backwards, after all, everything is expanding outward, if you collapse it, it seems to me that you should be able to come up with some sort of point of origin. Anyway, we'll tackle this when we get back from the break. Dr. Sean Carroll is our guest. And, of course, you're listening to Coast AM. Point of origin. Now, I'm certainly not in Dr. Carroll's league, but it seems to me that if we're expanding at an ever-increasing rate, that a computer could I don't know, it seems like it could take various points of information, measure the expansion, and then work backward and actually come up with a point of origin. So we'll pick up on that in just a moment. If he could just say that a little faster. All right, Doctor, welcome back. Now, what about that? If we can measure the expansion, even measure the increase in the rate of the expansion, it seems to me we could task a computer with looking at these various bodies and work backwards and come up with something like a point of origin.
Well, it doesn't really quite work that way as far as we understand, because there isn't any such thing as the point of origin. It's not that we don't know where it was. It's just that the expansion of the universe is something that happens everywhere in exactly the same way. So it's true that here on Earth we see different galaxies moving away from us, all in all directions of the sky.
Right.
But if you were on one of those other galaxies, you would also see all the galaxies moving away from you in all directions of the sky in exactly the same way. So the universe seems to us on large scales to be completely uniform. And when we say that the universe is expanding, we really just mean that the distance between every galaxy and every other galaxy is getting bigger. And that's not a statement about moving away from some point in space.
Right.
It's a statement about space itself just getting bigger and bigger.
Finally got it. Okay. And here's another one for you. If everything is expanding at an ever-increasing rate, then, unless I'm wrong, we measure the distant points of the galaxy with light, for example, from pulsars. Is that correct?
That's right.
Okay. Well, then what about light itself, which is moving, well, at the speed of light, right? And on outward, we know that because we see it 14.5 billion light years away or whatever. So isn't this same force affecting light? And if it is, isn't light eventually going to get pushed over its own threshold?
Well, what's going to happen is that for any individual galaxy, it will move so far away that the light it emits will never, ever get to us, even though we wait an infinite number of years. So we'll be able to see fewer and fewer galaxies in the universe as we wait longer and longer, both because their stars will stop shining and because they get so far away that the light is never going to reach us.
Okay. Stephen in Los Angeles, you're on with Dr. Carroll.
Yes, good morning, gentlemen.
Good morning.
I have a thought experiment. Suppose there was a particle immediately before the Big Bang. There was a single point particle. Is it possible that in a collider, while looking for the Higgs boson or whatever, we instead found this first particle, this God particle? And sometimes they call the Higgs the God particle, but I'm talking about the particle that actually was there before anything else. If we were to observe that in the collider, would there be any possibility that the whole universe would be annihilated to the pre-Big Bang state?
Well, there's two things. One is that I'm not quite sure what that would mean, what it would mean for there to be a single particle before the Big Bang. We think that there were many, 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 many particles as soon as the Big Bang happened. And it's interesting that there are only a finite number of types of particles. You know, ahead of time, there was no rule, if you didn't know anything about particle physics, that there weren't an infinite number of possible types of particles. But we think that the number of types is very small, but there's just many, many examples of them. And it's a big universe, and there are many, many examples of each different kind of particle. But the reason why we're pretty sure that nothing so dramatic will happen when you start colliding particles together at CERN or other particle accelerators is because, like we talked about before, this has already happened in the history of the universe. All the time out in space, very high-energy particles smack into each other with much higher energies than we're going to ever make, than we're going to make anyway at CERN. Maybe someday we'll get to those high energies, but we're not anywhere near there yet. So the things that we're doing at particle accelerators have already been done in outer space. It's not a new phenomenon for the history of the universe. The thing is that we're going to be able to observe it with exquisite care in a way that we haven't been able to do before.
Okay. And this has all happened without universally catastrophic results.
That's right.
All right. Jim in Bellevue, Washington, you're on with Dr. Sean Carroll.
Yes, I have a couple of hypothetical questions. I was wondering, let's say for the sake of argument, there was a black hole that was oriented in such a way that the jet from the black hole were to stream down onto the solar system. What effect that would have on us here on Earth? And the second question I have is, if a large brown dwarf size body were to move very fast so that it wouldn't actually collide with the Earth, but was to pass, let's say, within the orbit of the moon, what kind of tidal effect that would have on the ocean?
So these are good questions. I think that they're very different answers. For the black hole that is beaming stuff, in either case there's very good news, which is that the universe is a very sparsely populated place. This is bad news if you want to travel from star to star. They're light years away from each other. But it's very good news if you have some concern about running into some other celestial object. The chance that the solar system will be invaded by another black hole or a brown dwarf or anything like that is very, very, very small from everything that we understand about how the galaxy is arranged. But it could happen. I mean, there's a chance, even though it's small. So you're certainly allowed to think about what would it look like if a brown dwarf came into the solar system. Then that would depend a lot on exactly how heavy it was. Brown dwarfs are generally heavier than the planet Jupiter, but smaller than the sun. So Jupiter already exists in the solar system, and it has a tiny but measurable effect on the motion of the Earth and the Moon. If it came very close to the Earth, that would have a huge effect. I mean, it would wipe out life here on Earth. It would roll the oceans from side to side and tremendous earthquakes and all that. But the chances of that happening are really, really small. The chances of a black hole being anywhere close enough to Earth to have some substantial effect are even smaller than that. We think that the galaxy is full of brown dwarfs, but there are very few black holes compared to the number of stars. It's much more worrisome to just worry about if another star came right into the solar system. So I would worry about that more than black holes, but I wouldn't worry about either one of them very much at all.
The possibility of another star.
Sure, why not? There's 100 billion stars in the galaxy. They're all moving around. Occasionally they will collide, or occasionally they will pass by each other at very close range. But the point is that even though there are so many stars, the galaxy is a very, very big place. So these collisions happen very, very infrequently. It's not something to worry about in terms of the list of interesting things you should worry about. It's low on that list, but it's certainly something you can contemplate.
But probably would rather not.
I would not hope that would happen, yeah. That would be a disaster.
Marlon in Flagstaff, Arizona. You're on with Dr. Carroll. Hi.
Greetings, gentlemen. It's a pleasure to speak with you. I have two quick questions. My first question is regarding the concept of infinity. I don't understand the idea of saying how something without measure can be bigger and then bigger again, because to suggest bigger means that it was one thing and now that it's another thing. My second question is, why doesn't light puddle on the ground?
Could you repeat the second question? I thought I understood the first one, but the second one didn't quite.
The second question is, the sun is ejecting particles of light, photons.
Yes.
Why doesn't it puddle on the ground?
Why doesn't it puddle? Okay, so let's tackle that one. The short answer is that light is made of particles which always move at the speed of light. That's the rule. And they can move a little bit slower if they're inside some medium. So, for example, light moving through glass or water moves slightly slower than the speed of light. The speed of light really means the speed of light through vacuum. But light does not stay still. It does not collect. It will bounce off. It could be absorbed. It could be deflected. but it's not just going to collect in some area. It's not a liquid. It'll just bounce off.
Puddle. Yes.
Or it will not puddle.
Okay, and then he wanted some understanding of infinity.
Right. So that's a very good question, because when we talk about the universe expanding, it's natural to think of something expanding as something that is growing in size, and therefore you say, well, how big is it? And we don't know the answer to the question, how big is the universe? Yet we do know the answer to the question, how is it expanding? And it's a very interesting question. How do we know that it's expanding if we don't know how big it is?
Mm-hmm.
And the answer is, when we talk about how the universe is expanding, we're talking about the relative size. So we know that a distance to a certain galaxy is so and so many light years, and we know that it will take a certain number of years for that distance to increase by 10%. And in that number of years, the distance to every galaxy in the universe will increase by 10%. So the overall size of the universe can be some finite number that we don't know, or it could be infinitely big. But the distance between all the galaxies in the universe will increase by 10%. That's still a sensible thing to say. So we know that the distances between galaxies are getting bigger, even though we have no idea how far away the furthest galaxy is, or even if that's a concept that makes any sense.
Okay. Eddie, in Dallas, Texas, you're on the air.
Hi, Art. How are you?
I'm just fine.
Good. I think some of the confusion about the new planet, that it has water and it's all set up for life, is when it was first reported, the report said that they could see heat waves coming off as if heat waves were coming off of water. And the temperatures were in the 70s. And so that could be some of the confusion about why some people think that it's already set up for life that maybe we could inhabit. My second part is for the doctor.
Mm-hmm.
Are you there?
Yep.
Yes, go ahead.
Okay. I think that I use the KISS method. I try to keep it simple. When it comes to the universe expanding, that it's like if you took a flashlight and you at night or any day, and you put the light beam up into the sky, the light does not ever stop unless it hits something.
I don't think that's technically true. Is it, Doctor?
Well, light could certainly travel through space forever and ever unless it hits something, but there's plenty of things for it to hit. I mean, when we look at the leftover radiation from the Big Bang, that is light that has traveled basically unimpeded from when the universe was 400,000 years old to today, when it's 14 billion years old. But I'm not quite sure what the connection is between that and the expansion of the universe.
Well, but light at some point becomes completely undetectable, yes?
Well, what happens is as the universe expands, it stretches the light along with it.
Right.
So very high energy, short wavelength light becomes fairly low energy, long wavelength light. However, in the history of the actual universe so far, that stretching has not been so dramatic that anything has dropped out of our range of detectability. Eventually that will happen, but in the last 14 billion years it hasn't happened yet.
Okay. Ted in Texas, you're on with Dr. Carroll.
Yes, Dr. Carroll, how you doing?
Good, how are you?
I have a quick question for you, and then I'll hang up and listen to your answer. I heard a theory, and I just want to know if it's true and if you could explain it right quick. I don't know if I have the numbers right, but I heard that if you go into space with a rocket and you travel at the speed of light for 6 years, then take 6 more years to slow down, turn around, go 6 more years at the speed of light, and then slow down and enter the Earth, that in that 24-year period, you would be 3,000 years ahead. Is that true?
Well, that's not precisely true for the sort of nitpicky-sounding reason that you cannot travel at exactly the speed of light. You can travel very, very close. So the numbers you quote will be true for some speed, which will be 99.999 something like that percent of the speed of light, but not exactly it. But the basic lesson is exactly true. If you move out close to the speed of light, turn around and come back close to the speed of light, you will feel much less time to have passed than the people you left behind and have come back to see again. And this is something that was worked out over 100 years ago by Einstein and his friends, and we've been able to measure it because we have elementary particles that decay. They have a certain lifetime to decay. They decay, once every 1/1,000,000th of a second or something like that, and we push them up close to the speed of light, and suddenly they last for minutes or longer. And that's because their internal clocks are running at a different rate than we are here stationary on Earth.
Doctor, using certain propulsion techniques, is it not possible that we could launch something that eventually, with continued, not a great deal of energy used, but continued propulsion of some sort, would get close to the speed of light eventually?
Sure, that's absolutely possible. It's, again, a technology problem. It's not a violating laws of physics problem.
Right.
As far as the laws of physics are concerned, you can go as close to the speed of light as you want as long as you don't get there. So it's a favorite science fiction, sort of in the hard science fiction category where they try not to violate the laws of physics. A lot of people have written stories about ships that would travel between the stars, and they would travel close to the speed of light, and therefore when they got there, if they sent some people back, even though the people who made this round trip felt that a couple of years had passed, the people back here on Earth would feel that hundreds or thousands of years had passed. And that's exactly what the laws of physics tell you should happen. Someday, if we keep advancing technologically, that's completely feasible. That's very realistic. Hyperspace and wormholes and things like that are, well, maybe, we can't tell you they're not true yet, but it's certainly not within what we already understand. But traveling at 99.99% of the speed of light is something we do understand.
Okay, your book, Space-Time and Geometry, An Introduction to General Relativity. How long has that been out?
It's been out a couple of years now. It's a technical book for graduate students, so I can't in good conscience ask people to buy it unless they're graduate students, even though it helps my pocketbook when you do. But there's many, many good books out there on general relativity and space and time that tell you all these things at an accessible level, and I encourage people to learn as much as they can.
Any one that you particularly would recommend?
Well, there's a book by Brian Greene, who became very well known for writing a book called The Elegant Universe, which is an introduction to string theory. But there's actually a follow-up to that book called The Fabric of the Cosmos that teaches you some of the basics about general relativity, the arrow of time, and cosmology. It's very much about what we've been talking about on this show.
Mm-hmm. All right. Well, Doctor, our time is up. The show is virtually over, so it has been an absolute pleasure having you here, and no doubt we will have you back again.
Great. Thank you very much, Art.
Thank you for staying up with us, and good night, Doctor.
Good night.
All right, everybody. That's about it for this night. If you get an opportunity, it's quite a photograph I've got up there on the website, Art's webcam position at coasttocoastam.com. I think it's absolutely beautiful. And with that thought, I leave you with an absolutely beautiful voice. This is Crystal. Good night.